in the waiting room for just a little bit because I want to give everybody a heads up that this may in fact be a documented event. So if they're talking about personal things, I just want to make sure that everybody's good to go, that just a fair heads up. And then would one of you want to be co-host to let people in from the waiting room? Because I forgot when I decided to do this one, I forgot it was a waiting room scenario because committed to it. I'm just going to leave it as is. But would one of you, basically all you're going to have to do is let people come in as they join. So for the late arrivals. Keep in jail? That's a good point. Yeah, forget them. Okay, so you don't seem like a good candidate. Okay. Oh no, did I? Yeah. So that, I think, Anush, do you also have the power to change people's names? Oh, perfect. Yeah, so feel free to have fun at mostly Jonathan's expense. Okay, I'm gonna go ahead and share screen. I figure again, because it's Friday and wasn't ever supposed to be this, I don't know how many people will show. So with that in mind, I think probably going in about a minute here. And again, just want to take a moment. Jonathan, thank you for like stepping up above and beyond. And again, I apologize because we as a company have dropped the ball, and it's still I'm still a part of it, and I'm kind of bummed it's not as good as it always has been, but I'm going to do my damnedest to make it fill in the gaps as best as possible. And good things are on the horizon as well. So anyway, with that in mind, just appreciate it. And it's awesome you guys take care of each other. And never has a sign up, has a registration day been as much teamwork as it was this time. I mean, you guys are just downright impressive. And I seriously hope you stay in touch long after this class ends. I hope you guys stay in touch with each other and help each other out in the application process, because it could be arduous, it can be stressful. And when you have good people with you, it makes such a huge difference. Okay, I'll go ahead and get started then. So I assume this is going to be it for who will show. All right, starting in 3, 2, 1, and yeah, low key is good. And that's, oh no. Oh no. Okay, there we go. For whatever reason, hold on. This is, how embarrassing that this is. I gotta change pencil tips. Give me just a couple seconds. I'm so sorry. I need to exit on my iPad for a second. Talk about awesome professionalism. After giving a big speech about how we need to be more professional. Huh. It's fully charged. There we go, finally. Okay, now we're connected. Yep, how's that for professional? Okay, seriously, now we're on our way. So today, the whole goal of this lecture, as I mentioned possibly in a post, the main goal is to kind of give this as sort of the mentality of a pre-lecture, knowing full well you're going to see this next week. And that's my goal, is the lectures that are really tough, really time consuming. I'm hopeful this can be an alternative to reading and just a good way to think about and applying things. So just want to revisit the whole thought of why the heck you should be studying for the MCAT. So A, to learn everything in great depth so you can go to grad school on it, or B, learn the fundamentals so well that when you see a question, you can apply it instantly. Oh, okay, good call. Let me exit out. I do have that. Completely forgot to load it up. Bugga. I seriously, I have no idea why I'm brain farting on this one. But yeah, so it should be loading up right now. Huh. Okay, there we go. Yeah. And again, just want to revisit the thought that what I do is not actually a slide program. It's an animating program. So that page has screenshots. But okay, finally on the roll. Oxidation reduction. What defines oxidation? So if somebody asks, what is oxidation? What would you tell them? Loss of electrons. That's your fundamental GChem definition. Perfect. So that's how we're going to think of it in terms of this class. What happens when you lose electrons? What happens to your charge? Loss of hydrogen can also be it. Your charge increases. You can lose H's, H minuses, you lose them, and you've been oxidized. You can also gain O's, which means, did you guys just define multiple ways of describing oxidation? You lose electrons. That's the fundamental definition. But the cause of that, if you lose electrons for oxidation, you get more positive. You gain electrons, you get more negative. Perfect. So you could look at charge. That's one way. Gain the loss of hydrogen, especially for organic molecules, hydrogenation and dehydrogenation. Perfect. Gain of oxygen. So which one is going to be on your MCAT? The GChem definition or all the definitions? All the definitions. So it's important, although technically this is a GChem lecture, is there applications in biochem, molecular biology, OChem, even go as far as physics. And so whatever we learn has to apply across all sciences. And so as you mentioned, loss of electrons is oxidation. Somebody said Leo, gain electrons reduction. So somebody said Leo GER. I'm going to turn mnemonic into a little bit bigger mnemonic. Now, some of you may have learned oil rig. That works as well. I choose Leo because I have one extra piece in it. So Leo the red cat says GER. What this mnemonic tells me: lose electrons oxidation, gain electrons reduction. And where does reduction occur? At the cathode. So if I were to draw an electrochemical cell, just a really primitive one here, if I told you that electrons flowed from here to here, can you tell me a few identity questions? Is this my anode or my cathode? Let's see if our friend Leo the red cat can help us. So first off, is this electrode, the one on the left, gaining or losing the electrons as drawn? Losing. Okay, so this side is losing electrons. So losing electrons means this is the oxidation side. Where does a reduction occur? Reduction occurs at the cathode. So that means where does oxidation occur? Oxan, another animal. So maybe Leo the red cat was saying GER to an oxen. Could be, we don't know. Over here, we're gaining electrons, so this is reduction. So this is my cathode. Because this is a definition, I'm going to safely say this is true in every science, even though the rules of how they define electrodes, like anode and cathode, can vary. Oxidation occurs at the anode, so oxidation is always the loss of electrons, so the anode always loses electrons, cathode always gains it. So I want you to chalk this up to memory. This is always true. This is universal truth based on definition. Electrons flow alphabetically. They always flow from the anode to the cathode. So electrons flow from anode to cathode. So I get into the circuits lecture, I'm remembering this, electrons flow anode to cathode. And then they show an arrow pointing from the cathode to the anode. And I go, what the? And I fill in the profanity of choice, depending on my mood that day. So I'm telling you, electrons flow anode to cathode, universally true. What do we show in physics, just to make sure we're on the same page here? Do they show the flow of electrons, or do they have imaginary plus charges? In physics, they show the imaginary plus charge, the positive charge. So they show something called current. In physics, they would show current going one way, but a positive going one way is the same as negative going the other. So today we're dealing in reality. We're dealing with electron flow, but in physics, they might show cation flow. Okay, so I'm happy with this. Reduction occurs. Would reduction result in a buildup or a breakdown of material? Good job on the getting people in fast. Nice. This one will build up. So over time, the cathode will plate out and the anode will dissolve away. Need to get my spelling down pat. Dissolves away. Whew. I'm going to try to write it a little bit nicer. Okay, so I'm going to apply that to bio. Do we ever store any sort of molecule to use the energy later? Do we ever build up molecules? Like what? Give me an example of maybe what acetyl-CoA turns into somewhere. I don't know my bio, so you can help me out here. So a whole bunch of acetyl-CoAs, can I combine them into one massive long molecule? Perfect, fatty acids, exactly. So is that true? We build fatty acids from a 2-carbon molecule known as acetyl-CoA. We go from 2 to 4 to 6 to 8. Yeah, so what we mean by dissolves away and plates out, and I'm going to explain it. Let me finish this way and cycle back in because it's true for both of these. So what plate out means, and then what a fat buildup means. So when we build a fat, we go from 2 to 4 to 6 to 8. Is that molecule getting bigger and bigger? Sure, it's getting longer and bigger. Over here is a cathode, because as electrons start to build up here, can something like, I don't know, maybe copper or gold or silver, something in solution, can it come here and plate out? Can another copper come here and plate out? So I start building up reduction. Do all these metal, these cations start building up metal, and does the cathode get bigger and bigger and bigger as it starts plating out, reducing? So just like you're aware of in bio and in GChem, the same thing holds. In reduction, you get things to build up. Yeah, and notice I'm being careful. I'm not using the word precipitate, because precipitate implies it stays as a cation and turns into a salt. So instead, it's actually getting plated out. That's what we, instead of using precipitate out, we say it plates out. And the verb is a made up verb from just observation. It becomes part of the metal plate over time. Yeah, exactly. So, I mean, not to judge, I don't mean to be condescending in any way, but for those of you, and you know who you are, when you go to the nightclub wearing your gold-plated jewelry to try to pretend that you're something you're not, where did you make your gold-plated jewelry, Jonathan? Oh, shoot. I'm sorry I said it out loud. I'm so sorry I totally outed you on that one. But where do you put your copper chain, Jonathan, before you turn into a gold chain to go out nightclubbing? You put it the anode or cathode to plate out, to build a thin fake layer of gold on the surface of your cheap metal to fool people. I knew you'd get it right. Experience teaches. We believe you. We believe you. But if I put something here, it'll plate out. You put a thin layer. So whoever said that, perfect. You put a thin layer of metal on it. So what happens to the other side then? If this thing's plating out, what happens to this one? Every time the electron goes away, can, let's say, a piece of zinc, let's say this made of zinc metal, can zinc get oxidized in zinc 2 plus? Let me rewrite that. I'm sorry. So it's reasonable that zinc gets oxidized away, turns into a cation, well, this one plates out. Dissolves in solution, exactly. And up to a point, then maybe it'll precipitate out after that, but exactly. Okay, so let me take this one step further. Let's go back to bio. if something is an oxidative process, does it build up or break down? So generally, when we think of oxidation building up molecules or breaking molecules down. Perfect. Oxidation goes with a breakdown. Reduction goes with a buildup. So if I said fatty acid synthesis, it's a buildup. If I said beta oxidation, is that a buildup or a breakdown? Beta oxidation, breakdown. A little more detail, it's a breakdown of a fatty acid chain back into acetyl-CoA and gives you energy. Glycolysis is a buildup or a breakdown? Breakdown. It's oxidative. You're going from a 6-carbon chain to 2 3-carbon fragments. So you're actually breaking down. So it's not a full breakdown. You're not spitting out CO2 from it, but it's a breakdown. So let me ask you this. So if this is true, if what I'm telling you is true, that C6 going to 2 C3s is a breakdown. That means it's oxidation. That means it must be coupled with what? Whatever it is, it must be coupled with reduction. You agree? You have to have reduction to go with oxidation. Exactly. So I'm going to draw something here, and I want you to say, good job, way to go, I trust you. Or I want you to tell me that I've messed this up. So I'm going to say NADH and H plus go to NAD plus. Got that right, or I messed that up? I messed it up. That is an oxidation. That lost H's. So how about now? Is that right? Is that an oxidation of carbon chain coupled with reduction of NAD plus? So in other words, is that true? Does glycolysis ultimately spit out some NADHs? You invest a couple, but for net gain at the end of it, by the time you're spitting out pyruvate, are you also spitting out NADHs when you undergo glycolysis? Perfect. And just out of curiosity, how many had a professor that made you count the ATP or count the NADHs or count these quote unquote energy molecules? Every professor on the planet loves that question. For whatever reason, they are hell-bent, they got to ask it that way. So your job, recognize energy molecules. Stored energy can be A, reduced molecules, FADH2, NADH, etc., or long-chain phosphates, pyrophosphates, like ADP, triphosphates like ATP. Ooh. Yeah. And and if you don't mind my quote, I got a direct message. I want to say it because I think your comment is universally true. You don't mind. So somebody said, we just learned glycolysis yesterday, but somehow I still have no idea what it is. And that's just something I want to address. It's gonna pop up next slide, what it is. But your job is to know a little bit about a lot and figure the pieces out as you go. You don't have to know things in intimate detail. And for anybody who's taking the MCAT, would you agree the passage gives you more details than you'll ever need? You have to know the nuances, how one thought applies to somewhere else. So if you learned in glycolysis that phosphorylation is coupled with energy, that anytime you have a kinase, anytime you have a phosphate being transferred from one point to another, some energy is involved. So if you know that in one pathway, is that going to be true in probably other pathways where you see it? You do not have to memorize any pathways, but hear me out on this one. Know your key players, know the key steps, know what you spit out, know how much energy is involved in it. So in other words, the details, no, the big picture, yes. And I personally think, for me, I walked in knowing one pathway. I chose glycolysis to know it inside out. I could tell you anything at that point in time about those 10 steps so that I could apply it to somewhere else. But the important things, if you recognize what's going on in a step in glycolysis, can you apply it to electron transport chain? Or can you apply it to some weird mechanism you've never seen before? So be careful. The word memorize means be able to draw it from memory. Don't do that. Instead, know what happens. So in glycolysis, for instance, no, are there phosphorylations? Like, for instance, a good question, what is the very first step of glycolysis? Um, Glucose is glucose 6-phosphate. You put a phosphate on it. So a couple questions for you. Number one, does that involve energy? Involves a kinase, exactly. Why do you call it a hexokinase and not a pentokinase? 6 carbon sugar, perfect. Why do we phosphorylate it? Is it because we need the energy, or because now we've put a ball and chain on the ankle of that glucose, so it can't go anywhere? Ball and chain, we've locked it up, can't go anywhere else. But one subtle nuance: how many learn that we break down alpha and not beta? We break down glycogen, amylose. We do not break down cellulose. Okay, we don't have the enzyme, we don't have cellulase enzyme, but there's more to it. Specifically, what kind of glucose gets phosphorylated? Alpha or beta? D, that is true. D, I should have said. We digest our sugars. So natural sugars have to be D, but even more specifically, that first phosphorylation step is alpha. So if we have a beta, it won't get phosphorylated. Beta can go back out, go in, go back out as much as it wants. But eventually the beta will be converted to alpha. When alpha comes in, it's clamped, it's locked, we're on our way. We have it, we have what we want. The chain gets opened shortly after that, so it's irrelevant. But the enzyme, that kinase, actually specifically recognizes alpha to anchor it down so it goes in or stays in the cell. So now that you know the why, can you apply that concept to other pathways? So if there's another molecule that goes in and the first step is phosphorylation, is it a reasonable leap of faith to say it's probably locking it into position? It's probably keeping it there. And so when you say memorize the pathways, I say understand one pathway incredibly well. The more that you know, the better. But don't just memorize the words and the details. Figure out why you do stuff. So I don't know if I've answered your question or I've just stressed you out, but if you know why, you can always figure out other things. If you know what, you know one thing. Okay. Oh yeah. Okay, wait a minute. You're telling me occasionally there's stressful moments where you sort of blank out and freak out a little bit? Oh, I don't believe that. I believe it's a totally relaxing, wonderful experience, almost like vacation. You're gonna sit there and you're gonna think, wait, where's all like the lobster being delivered to me? Where's my foot massage? Yeah, and the thing is, seeing the big picture and how they apply. And I think the one saving grace about biochem that I have to really tip my cap to, and that is, are a lot of the enzymes named for what they do? Yeah. So unlike chemistry, where we name things after ourselves because we're arrogant, they name after what they do. And yeah, it is a thankfully. So is a hydrogenase enzyme responsible for reduction or oxidation? Getting it kind of back on this track. So a hydrogenase enzyme is responsible for oxidation or reduction. So I should probably spell this out. A hydrogenation catalyst. I might have spelled this a little hard to see, but what does a hydrogenation catalyst do? It adds hydrogen. Perfect. Gain of H, somebody mentioned it earlier and I've already forgotten, but the gain of H is oxidation reduction. Reduction. That said, enzymes can carry forward or back out, but typically we name it for what we observe them doing. So dehydrogenation, oxidation, hydrogenation, reduction. I'm double check, make sure I said that right. Dehydrogenation is oxidation, hydrogenation is reduction. And the thing is, you nailed it. You just have to hammer it and honestly, get a mantra. Leo the Red Cat Says Grr is one of many. And hopefully that's what this page, when we're done with this page, you have all the foundation of what you need. Okay, over the map, I'm gonna erase this in 3, 2, 1, done. Oxidation, when you lose electrons, we mentioned your oxidation state goes up, you get more positive. When you gain electrons, oxidation state goes down. Subtle difference, but difference between an oxidation state and a charge. A charge is an actual measurement of how many electrons you have in excess or shortage. Oxidation state is defined as if the world spontaneously broke apart and everything went into ions, what charge you would have if you were an ion. So charge truly is an ion, oxidation state, if it were to become. Real subtle thing that sadly I didn't realize till later in my academic career, when we put this sign before the number like +2, that's an oxidation state. When we put number first, it's a charge. Yeah, and they're often the same number. They're often interchangeable. But calcium has a 2+ charge, but a +2 oxidation state. But everybody see what Aruna just said there? Absolutely golden information. A lot of times they're the same, especially if an atom's all by itself, they are the exact same. Okay. Loss of H, somebody mentioned oxidation, gain of O, so I just want to emphasize that. And then on the other side, so let me show you an OChem reaction and you tell me what's going on. That's a terribly drawn R. So which are which? Which is which? From aldehyde to acid, oxidation reduction? Oxidation, perfect. Because you've gained a bond to O. You didn't actually lose H's, you gained a bond to O. What about to this alcohol? Gained H, so reduction. You ended up gaining an H on the O and an H on the carbon. Carbon used to have 1, now it has 2. Okay, I'm going to erase this and ask you a related question, but now you're going to play biochemistry for me. That's a 2. What is coupled with this? Alcohol dehydrogenase or alcohol hydrogenase enzyme? So what is involved with this? Alcohol dehydrogenase or alcohol hydrogenase? Alcohol dehydrogenase. Why do you say that? Explain me why that's the answer. It's an oxidation, dehydrogenation, you're losing H's, and you're just losing H's. It's kind of in the name. Alcohol losing H's, alcohol dehydrogenase. Again, thank you, biochemistry, for making my life easier, for naming exactly what it is. But up to you, but I might put then dehydrogenation, hydrogenation. Just add whatever you can. And then the last thing I want to put up here, I'm going to clear this reaction in 3, 2, 1, gone, is anabolism a buildup or breakdown process? I can't remember. And it's funny, I was watching baseball last night. You think watching baseball, I should know all about anabolic steroids. And how many do remember it because of pro athletes? Anabolic steroids build you up. So anabolism is buildup, which means anabolism is a reductive or oxidative process. Anabolism, reductive, perfect. On the other end, catabolism is a breakdown. Some are okay with this. What? Huh? Just reduction. So fatty acid synthesis, all those things, we build up molecules. Not, and I want to be careful. Like there's certain builds that we're built, like we take glucose and make a longer chain. That's a dehydration. Gain and loss of water is not redox. But when we build up longer fatty acid chains, when we store longer molecules, when we build carbon-carbon bonds, make it longer, we're building up. So anabolic builds things up, catabolic breaks things down. Oxidative processes break things down. So does that, I mean, does it make sense just more of a nomenclature thing than anything else? And I think the answer to why is kind of, I don't know why they named it that way. Because I'm going to do something that is probably the worst thing to do as a teacher, but raise a question of something that bothers me. But just in case it bothers you, I don't know why cat would go here and and would go here, I would have named them differently. But it seems to me there's a couple things that are backwards in redox. And we think of anode, but it's wrong. Anabolism actually is something that would happen at the cathode reduction. Catabolism is something that happened at the anode for reduction. Counterintuitive to me, just like oxidizing agent and reducing agent are named for what they do, not what happens to them. Also a little counterintuitive. I don't know about you, but this bothers me. But you know, after enough time of just saying it over and over in my head, I just sort of accept it. Okay, time to play, name that reaction. Would this reaction ever happen? Is this something that really could happen? I'm not sure what it is. Teach me. Disulfide linkage. So I took two cysteine thiol groups and combined this. I'm going to tell you this is a reduction. You're going to say, right on, I'm doing well. Why are you saying I got it wrong? Melody, what have I done wrong? Ah, lost my H's. So oxidation. Okay. So now I'm going to mess with you because again, that's where I get job satisfaction. That is definitely oxidation. You're absolutely right. So if I wanted to go backwards, would I need to add something to this that was rich or poor in H? So now I'm going to mess with you. I have a disulfide linkage. I want to break it and turn it back into the original cysteines. The compound I'd react this with would be something rich or poor in H's. Has to be rich in H's. So I'm revisiting this from our very first amino acid lecture. I want to just, I'm doing this one because it's a shorter chain to draw, but I'm doing beta-mercaptoethanol. But again, just want to emphasize, you can make a bond there, lose that bond, make a bond, lose that bond, make a bond, lose that bond. So you now will end up, when you reduce it, with the two beta-mercaptoethanols connected to each other, and then the cysteine residues back to where they were. So hopefully that seems okay. So in every reaction, if you're doing it from an OChem perspective, you have to have something that has the H's, something that's missing the H's. Missing the H's has the H's. H's simply get transferred in a redox reaction, in this one. Okay, erasing this in 3, 2, 1. Tell me about this reaction, what's going on? So can I do it by gain and loss of O's, gain and loss of H's? Or is this one where I have to do according to oxidation state? I luck out. I could get it by O's, but I want to be really, really careful. So what is the oxidation state of O by itself? -2. So if I have 2 at -2 each, what's titanium? +4. And then this one's also, I think, +4, isn't it? Because chlorides are -1 each, so -4, so it must be +4. I did great on this one, or I messed this up. What did I mess up? What? So why is it +2? What have I messed up? Oh, Melody's got it. I completely ignored the charge. The sum of the oxidation states collectively has to equal the charge. So in this case, 4 at minus, but overall 2 minus. So this is +2. So that means that's also oxidation, or is that reduction? Overall reduction. Perfect. One last one. Very common in OChem. The quinone and hydroxyquinone. From just this picture, can you tell me oxidation reduction? You actually can. This is a lucky case where you can. So Fabiano, why are you saying oxidation? Oh, is that total peer pressure? Is that the Ash study in action, Melody? Totally pressured you into it? Feeling pretty solid about that? You lost H's. Perfect. Oh, okay. Yeah. So really good question Alex presented. Are there cases where a reaction can be classified a couple different ways, redox and nucleophile, electrophile? And the problem is everything in OChem is a case of one molecule attacking another. Two things can't come together unless they move. At least one of them has to move. So in OChem, for whatever reason, we always accuse one of being the attacker and one of being the victim, the one that's getting attacked. Nucleophile does the attacking, lone pair first. Electrophile just innocently there gets attacked with this lone pair. Just what happens. So if you wanted to, you could potentially describe this reaction as a nucleophilic attack. You could describe this H as being a nucleophile and coming up that way. Definitely true. So is this a nucleophile? Sure, this hydride nucleophile is attacking. But the minute I do that, have I now overcomplicated? I made both a reduction reaction, I'm looking at from one perspective, the gain of H. Am I also, though, complicating it by now saying it's a nucleophilic reaction? So they can all come together. A nucleophile can be a base, a nucleophile can be a reducing agent. It can classify as different ways. Might be a good idea actually to try to separate them into two categories, knowing full well I can have something be described by more than one thing. So you could describe this, oh, it's a reducing agent. I'm going, no, that's a nucleophile, which opens up the door to the questions they sometimes ask. This can be classified as all of the following except a Lewis base, a reducing agent, a nucleophile, an oxidizing agent. So can things be multiple categories? Can have some carry multiple labels? You bet. And I don't know if I've answered your question with this great answer that makes you feel better, or I've just made you go, shit, more stuff to know. I'm assuming it's a balance of both, but you have to, within the context of the question, deduce what exactly they're looking for, how they're looking at this, how they're addressing it. But excellent question. And your question is going to turn into multiple choice answers. And so, again, I apologize because I don't think I've answered your question with a solid answer, but I've talked a lot. So either I'm a good politician or this is one of those questions that's hard to answer. It's kind of a ubiquitous question of all the things covered. Okay. So big things. Can you recognize from bonding loss or gain of H? Can you recognize from formula loss or gain of H? And can you look at oxidation states? Yeah, and you just put the perfect word in there, organized. The more organized you are with the random facts, random definitions, the things you know, the quicker you can recall it, the quicker you can apply it. And that really is. And if there's anything I think Anki is great for, is that it's organizing things. And again, it could be information overload. You need to be careful with that, but helpful. Okay, clicking on 3, 2, 1, and again, I want to apologize on behalf of all chemists everywhere who defined it this way, but reducing agents themselves get oxidized. Oxidizing agents themselves get reduced. How many have had to say that to yourself over and over and over to remember it? How many agree it's just, for whatever reason, it does not stick? I mean, for me, I literally have to say these two things over and over. Leo the Red Cat says GR to an oxen. Reducing agents get oxidized, oxidizing agents get reduced. I have no pride. I'm going to say it over and over and over because I just have to start from ground zero. It's named for what it causes, not what happens to it. So reducing agents, if they get oxidized, should they be rich in H or poor in H? Okay, so I'm going to wait for a few more votes. And do most of you know what the ash study is? I keep referencing that whenever I ask questions because it's total application of it. So a little psych-soc thing, but how many are familiar with what the ash study is? That whole conformity thing that once you see one answer, you're more apt to go along with it. So that's the one thing. The chat box is just the living ash study, and I hope you guys just break away. But if it's getting oxidized, it has to have H's to lose, or if it's going to reduce something, reduction is a gain of H, so it is a thing that's going to have to provide the H's the other compound gains. So you are a supportive role. You're an agent causing this. You must be rich in H because you have to have H's to give away. Oh, yeah. You know, I don't necessarily suggest taking MCAT with your eyes closed, but I gotta admit, sometimes closed eyes do help in seeing things. Weird as that sentence is. Close your eyes to see clearer. I remember somebody telling me that, and I was thinking, okay, you're gonna kick me in the head when I say that. And I know, but okay. Rich in H, poor in O, they have to have O. Channel your inner chemist. Yeah, so the reason it is rich in H, so let's consider if it's getting oxidized, then which thing can get oxidized? NaBH4, can that go to BO2? Or NaBF4? Which one can act as a reducing agent? The one that has H's to give away, or the one that has no H's to give away? The first one has H's to give away. So in order for this thing to be oxidized, to lose H's, it has to have H's to lose. So it's really weird. And I'm telling you, this is really hard to see. Yeah. You know, Stephanie's analogy is spot on. And again, how many are huge on analogies like that? So excellent. That is a perfect one. So I'm going to, Stephanie, if you don't mind, I'm going to modify it. But yeah, if you're walking down the street and people are asking for money, you have to have it to give away. So you are getting robbed, you're getting your money taken, whatever, but you have to have it to be able to give it away. So excellent. So I know for everybody who's jealous, you're just gonna have to emotionally deal with it. But that's the star for Stephanie. Good call. That's an excellent analogy. And well deserved. And these are the kind of things that, again, how much pride do you have? Just screenshot the star. No pride whatsoever. Whatever way I get a right answer, I don't care. I do not care. If I get a right answer and get a point on the test, I'm good. I'm so over the having to sound like a scientist. I just want to get right answers, damn it. But you have to have it to lose it. Okay. Let me go ahead and erase. Oh no, I'm so sorry, Stephanie. Screenshot your star. 3, 2, 1. Oh, sorry. Oh, it hurts. So fleeting. Okay. Oxidizing agents have to be rich in O. They have to give O away. They have. Why would they have to be poor in H though? That one's confusing me. Why would an oxidizing agent be poor in H? Exactly. It has to be able to get reduced. So the same thing. If you don't have any money, you have to be poor in it in order to be able to accept it. Yeah, or it's the opposite. So you mean to tell me if you know one, you can fake your way through the other? Is that true? How many went through all of base chemistry that way? A base is something that isn't an acid. And honestly, how many of you think only in terms of acids and you fake your way through base? Huh, nobody's confessing? Yeah, I think we all think of acids. Same thing. If you know one thing, then you have actually learned its opposite without spending the energy to memorize it. But compounds that you should recognize, some from OChem, some from biochem, but notice the common theme, all of them rich in H's, all of them rich in O, or poor in H. So rich in O, peroxides, peroxy acids. And even though you may not recognize these reagents, what they do chemically, that's fine. If you recognize chromate is an oxidizing agent, rich in O, permanganate, rich in O, ozone, rich in O, peroxy acids. I definitely think you should know NADH, FADH2, NAD plus, FAD. Those are critical. But how many are okay with this page then? It's like, honestly, just stuff you have to just through practice get familiar with, or through just processing it, get it memorized. So these are our rules. And just want to revisit, is this only true for GChem, or have we just done GChem, OChem, and biochem? All of them. So when you learn something that's a universal topic like this, it applies across the board. So don't just know it in the context of GChem or OChem or bio, know it in all of them. Okay, clicking. Glycolysis. We mentioned that earlier. Glycolysis is an oxidative process. It's a breakdown. So if glucose is getting broken down, it's being oxidized, does that mean we need to add an oxidizing agent or reducing agent to make it happen? Oh, I hate this question. So if you're feeling uncertain, join our party. So if glucose is getting oxidized, that means the other compound must be getting reduced, which means it is a, what kind of agent? I'll do you a favor. I'll write the word agent. You just have to figure out what it is. Oxidizing agents get reduced. Honest answer, how many had to work through this? How many had to really think your way through it because of this dang definition being counterintuitive? So glucose getting oxidized, so glucose is actually the reducing agent. So this is one of those cases, can't lie to you that saying this is easy, this isn't. This is one of those things that because of the wording, you always have to think, like you think and process your way through. And how many would agree it was an effort to figure all this out? But once you made the connections, if this is oxidation, it's coupled with reduction, got that. Oxidizing agents get reduced. So if this is an oxidizing agent, glucose, which is getting oxidized, versus a reducing agent. It all ties together, but how many agree it's an effort? It's arduous to be able to figure this out. And that's fine. You know, that's also part of my study process, to know that, you know what, I'm gonna have to spend a little extra time thinking when I come to these sorts of problems. And as long as I know that in advance, I'm emotionally ready. I'm gonna be good to go. This is gonna work out for me. Okay. Yes, everybody read what Melody put? That's exactly the connection. If glucose is getting oxidized, the other one is getting reduced. And so therefore the other one must be the oxidizing agent because the other one is getting reduced. Oh, you know what? This is going to be kind of probably bad to say, but the honest truth is I've been teaching this for over 30 years and I still have to say it in my mind every single time. 30 years and I still haven't gotten comfortable. So you say, how do you get familiar? Talk about it for 31 years. I'm pretty sure next year is going to be the year where it totally hits for me. Yep. So the process is always going to be this. Identify one thing you recognize. So for me, what I recognized was glycolysis is a 6-carbon glucose residue turning into 2 3-carbon fragments, 2 pyruvates. So it was a breakdown. Because glucose got broken down, that was oxidation. I therefore know if this is oxidation, the other reaction must be reduction. So if this is reduction, oxidizing agents get reduced, reducing agents get oxidized. So because this is getting reduced, I'm adding an oxidizing agent. And here, this must be a reducing agent. So going one step further, oxidizing agents are rich in H or poor in H? Poor in H. So that's my NAD plus. That's my poor in H species. lot of work on this one. Yeah, and honestly, and this is the feedback for, I'm sure all of you are going through, how many like, oh my gosh, this is scrambling. The best way to deal with something like this is be really systematic, go step by step, do not rush. Break down, so it's oxidation. If it's oxidation, it's coupled with reduction. If it's oxidation, reducing agents get oxidized. So the other thing must be an oxidizing agent. You can make the connections to other things. As long as you know one starting point, then you make all your connections from there. And that's how you have to do it. This is the thought process to go through. And again, not all that terribly simple. Okay, I'm going to erase because something's going to come up on the screen real quick. 3, 2, 1. Going away. So glucose is getting oxidized, so it needs an oxidizing agent, meaning it is getting oxidized, so it's a reducing agent. So it needs to react with an oxidizing agent. Oxidizing agents are poor in H. So that's why you have to have something poor in H going to here. And just a note of interest, if it's a carbonyl in biochem, it's NAD. If it's an alkene, it's FADH2 or FAD. Just like certain reagents react with different molecules, but NAD typically goes with carbonyls. Just that's like that extra little bonus thing. I'm going to ignore that aspect of it and just know that NAD+. Okay. Fatty acid synthesis, I mentioned that one earlier. We take acetyl-CoA and we add it to another and another and another and another. So you're building this long fatty acid chain, 2 carbons at a time. So maybe you're up to 12, 14, 16, 18, some even number. So if you're building it up, fatty acid synthesis, a synthesis pathway is a buildup, so it's reductive. So therefore, what do you need to couple it with? If it's reductive, that means it is the reducing agent or oxidizing agent. It is the ox agent. So I need to couple it then with a perfect. Couple with the reducing agent, something rich in H. So if I were to show this one step, I've added one acetyl-CoA to another, and now I'm going to reduce this carbonyl down to an OH in one of the steps. So I'm going from a 2 bonds to O to 1 bond to O situation with no H, with an H and an H. So this is reduction. So the other molecule has to provide the H. Carbonyl, so I normally would say NADH, but reality, just note of interest, this was actually NADPH. So just for what it's worth. Hopefully this seems okay. Reduction equals buildups. Huh, I'm sorry, I'm not seeing the moniker right away, but reduction equals buildup, breaks equal. Oh, okay. Yeah. What is oxidizing agent here? Good question. Oxidizing agent here is the acetyl-CoA. So that one is adding to whatever the chain is over here. But the overall, this group going to the chain like that, that is your reducing agent. Okay, I want to mess with you. So forgive me on this. 3, 2, 1. I don't know how messing with you this is. Got a B vote. Got a C vote. Got an A vote. And so a couple ways to do this. Number one, how many of you memorize all the ingredients of what you eat? How many read every package in the world for how much energy you get from it? So your nutrition fanatics? Probably not. That's option number one. Option number two is for you to tell me what you expect in this pathway. It may go to methanol, it may go to methanol, it may go to acetic acid, and eventually CO2. But how many agree this is the most reduced form of carbon? This is the most oxidized form of carbon. How many would bind that? That's just kind of the way nature works. Fully reduced, all the H's, fully oxidized, all the O's. Overall, do you get energy out or do you absorb energy? So when we combust our energy, our molecules, we eat whatever it is, we combust and give off CO2 plus energy. So which one would you put in your car? Which one would you have coming out of your burner on your oven? The reduced form or oxidized form if you want to get energy coming out of it? The reduced form. Every step of the way, releases energy. So when you oxidize things, you release energy, which is why do we store fats? We store fats to release energy or to store energy. Store energy. So that means this, in essence, can be thought of as stored energy. So if you ever look at a label, you'll notice carbohydrates, are those fully reduced or do they have some O's? They have lots of O's, so therefore they give you lots of energy, a little bit of energy, or no energy. Yeah, only a little bit. Hydrocarbons give you a lot, sugar gives you a little bit. So carbohydrates and starch is kind of the same answer. But how many have ever looked at a packaging and they say carbohydrates are about 4.5 calories per gram? I mean, how many, does that number look at all familiar to anybody who's reads the label on there on what they eat or drink? And if not, that's fine. I mean, it's just aiming for that. So which gives you the most energy? Which one do you put in your car to make it go? Yeah, proteins are around 4, carbohydrates around 4, fats are around 9. So the most reduced molecule, the one with the most H's, is the one that's going to be able to give you the most energy. Okay, so let's go thinking about our car for a minute. Oh, it helps so much when you see the big picture that way. Yeah, so everybody see Marissa's question? How do you answer that? So is ATP an energy molecule? Sure. So did you just ask the same question and word it differently? Meaning, are you secretly an MCAT test writer hanging out with us? Yeah, what Melody just said is absolutely perfect. So that's why. So then I have a question for you. So this is totally true. I'm completely telling the straight, honest truth on this one. So explain to me 2 things in life that are true. Number 1, do we store glycogen? I mean, is glycogen a form of energy for us? So do we do it A, to get a lot of energy, or B, to get quick energy? Quick energy. These are really hard to break down. These processes are very hard, but once you get here, it's easier. So I get less energy from carbohydrates, but I get it right now, dang it. So let me go back to this. If you look at the gasoline you put in your car, it'll likely be this molecule. Plus, you ever seen on the gas station thing, they say ethanol's been added, or they might say it's oxygenated gas? Oxygenated gasoline means they simply put ethanol. Why are they adding ethanol? A, they're trying to rip you off. B, they want to give you more energy. Or C, because it's partly oxidized, it burns faster, although it gives me less energy. Pasta. Pasta is here, get a lot of energy, but it doesn't last for very long. So why do they put ethanol in your gasoline? And how many next time you go to the gas tank are gonna, or get gas in your car, are gonna look at the thing and say, damn them, they're cheating me. Main reason? More in the middle of the chain, it's right around here probably. You get less energy, but it's released quicker. Exactly. So what you end up having, if you don't have it, what they found is this, yeah, you get a lot of energy, but it's really hard to burn. How many have ever been behind a car that you can smell the unburnt gasoline? Usually they're the older cars that don't prime their gas. They don't mix it with O2 and pre-burn it a little bit. It smells awful. They're wasting energy by not burning it. By putting just a little bit of ethanol, the ethanol catches fire, it gives you a little bit of heat, which in turn gives you more energy to make the activation energy to make these go. So 10% of this with 90% of this makes it so you burn this more completely. Okay, are we talking the exact same thing here as we're talking here as we're talking here? Are these all the big picture, the same thing for redox? And it's really cool when you see the big picture. Shopping at the gas station, to burning methane in your stove, to eating foods, you're still coming up with the same basic energy scheme. So good amount of energy, good amount of energy, good amount of energy, huge amount of energy, the most reduced. Oh, the reason ethanol is important, if you don't add ethanol, this actually won't be able to catch fire. So let's say this burns at 300, just toss a number out there, and this burns at 150. When the spark ignites at 200 without ethanol, it's not quite enough heat, so this won't burn completely. But if it ignites at 200, this catches fire, gives off heat, and turns it from 150 up to 300 or so. Yep, and the answer is fats, exactly. Yeah, after all the things gone off. So hopefully it seems okay. So glycogen doesn't give us a lot of energy, it gives us quick energy. Ethanol doesn't give us a lot of energy, it gives us quick energy. But the hydrocarbons are the ones that give you lots of energy, but they're a pain in the butt to burn. Okay, I'm going to erase everything I have here. I apologize for fat thumbing you. But these are the same answer. Fats are the ones that are most reduced. So how many see this as a big picture question, not a specific, do you know the minute details, but is this more of a big picture question? Hopefully, okay. And just out of curiosity, do we use sugar to get energy in our body? Ah, perfect. And that's what I'm hoping, and that you can step back from the details you were always taught in school to see why are you doing it. So now I have a little bit bigger appreciation for glycolysis. Is glycolysis one of a cascade of different pathways that collectively convert glucose into CO2? I mean, somehow, some way, is glucose eventually turning into a bunch of CO2 and am I getting energy out of it? Okay, you're getting all that energy immediately, or are you getting it in little chunks so it's easier to use and less wasteful? You get in little chunks. Excellent question. Fats and carbohydrates, or proteins and carbohydrates, are almost identical because if you look at how oxidized they are, carbohydrates have a bond to O for every bond to H. So it's kind of right in the middle. Proteins have this, but after that, degree they have, etc. So if I start considering what they are, they're oxidized like the sugar, but they're reduced here. So they're really, really close. To the best of my knowledge, it's like one's 4.5, one's 4.4. So they're all kind of a little bit oxidized, a little bit reduced, a little bit reduced, a little bit oxidized. So they're about the same. But fats give you the most energy. But good question. And these are the things, again, I hope all of you, as you study more and more and more, you start asking, what about the other answer choices? Because that's where questions evolve. Yeah, so see what Brooke said? If I were to predict, they would instead say, here are some numbers, and which protein or which sugar would be the best for a quick burst of energy, or which one would burn at the highest, or which one would give you the greatest heat release in a calorimeter, or something like that. And they'd make you analyze numbers. But those two are really, really close. Okay. I'm sorry, back to just plain old GChem. And honest answer, how many of you enjoy chemistry a lot more when it's applied to bio? How many does it just click in a better way and you can see it because it's in your interest area? Then I ask you to always do this. Do bio examples of chemistry questions. So when we start talking about gradients, ion gradients, I can do it in GChem, but how many know it more for the kidney, urea gradients, than anything else? Or there are other areas, but if you know it there, perfect. What is a kidney stone? Going off on a tangent, but just this big picture, studying for the MCAT. What is a kidney stone? It's a calcium salt. It's a rock that basically builds up. So it could be calcium oxalate, could be calcium with another protein derivative, could be calcium carbonate, could be, that's rare, but I mean, there are different types of calcium stones that build up. But yeah, so calcium precipitates out in your kidney. So what do you think the cause of it is? I mean, you took solubility. So solubility. Okay, so something to do with equilibrium. So you would suspect these calcium salts have a high or low solubility if they're precipitating out. So the KSP actually just the opposite. It's really low. So calcium salts, calcium is 2+. A 2+ charge is going to be really hard to get in the water because a full 2+ charge is going to form a really strong lattice. So calcium typically precipitates out, which is why it's great for bones, great for teeth, because it doesn't dissolve. I mean, you agree, in the rainstorm, if your calcium dissolved, you'd be in trouble. So calcium is one of the hardest things to move around our body. The problem is then, where are you in your body? Where's the area where you're removing water and concentrating all your salts? So is there any one part in your body where you're reabsorbing water and therefore you're taking what might be a reasonable concentration and suddenly making a higher concentration of impurities? Perfect. So where are you going to get precipitation? What part of your body is the most likely spot to get precipitates? Kidney. Hence, what's a kidney stone? A kidney stone is caused by having borderline soluble salts that when you reabsorb your water, they precipitate out. So what's the best way to prevent kidney stones? I mean, as simplistically as you can look at it from a chemistry standpoint, stay below the saturation point by either A, having lots and lots of water, hydrate, plenty of water, then even when you reabsorb water, it's not going to make it so low that it precipitates, or get rid of whatever provides calcium, or get rid of whatever provides the counter ion in your particular kidney stone. So mine, for instance, was oxalate. So it just, by bizarre thing, I had this terrible habit of drinking lots of iced tea and having a protein-rich diet. That's what they said. So my oxalate was a salt that just calcium oxalate that formed. Just kind of interesting. Okay, the big picture. How many find that solubility is far more interesting applied to the kidney than it ever was with KSPs and numbers and calculations? Much more. But now I want you to take the fact that you know a kidney stone is rich in calcium and tell me, what do you want to build your freeways out of? So freeways are a precipitated salt. We make this artificial rock, if you will. Would you make it out of a sodium salt, a potassium salt, a calcium salt, or magnesium salt? So what would you make cement out of? Calcium. Perfect. Calcium is calcium oxide, amongst other things, are prevalent in what's holding cement together. That's a glue that's holding whatever sand or mixture or whatever rocks you're putting in there. But does that suddenly make more sense because you understand kidney stones? And the moral to the story is, if you can see it in one situation, can you apply it in a new situation? The more you can do that, the better you're going to be on this test, but just in life in general, the more you make connections. Okay, that aside, now I have to apologize that biology is going away for a while, and now it's just straight out GChem. Yep. Well, if you like calcium structures, it sucks, but I hate statues. I hate beautiful artwork. I hate freeways. I hate buildings. I love acid rain. It's great. I hate fresh crops. I hate things that grow. So, so here we're loving it. Perfect. So reducing agents get oxidized. Perfect. So magnesium is starting by itself, which means what is its oxidation state to begin with? 0. Perfect. What is it in the end? Perfect. So it is the thing getting oxidized. So number 1, does it have to be a reactant? Yes. And number 2, it has to be the one getting oxidized because oxidizing agents get reduced. Your answers were phenomenal, meaning how many are saying to yourself, oxidizing agents get reduced, reducing agents get oxidized? How many is this just what you have to do every single time? Say it over and over and over. And again, I ask you the question, how much pride? 0, none, nada. You have no pride, get right answers. So time to mess with you. How many have been asked at some point during your OChem travels, is this a reducing sugar? Have you ever been asked that question? Is this a reducing sugar in biochem or OChem? That's me screaming at that question because always bothersome. So if it's a reducing sugar, what I want to tell you is really then, I'm going to make it a longer word. It's a reducing agent that happens to be, I'm going to fail so miserably at this, happens to be a sugar. I failed so miserably. I'm going to do this again because this, I think this is, I'm trying to make a point and I just butchered it. So I'm going to make that exact same sentence, but I'm going to draw it better. It's a reducing agent that happens to be a sugar. But unfortunately, they only saw this part of it. That's what I was trying to say, to be so cool and funny. But they forgot the middle part of this. So reducing sugar is reducing agent, happens to be a sugar. Reducing agents get oxidized or reduced? Perfect. Reducing sugars get oxidized. Okay, where this comes from, what you're supposed to know is recognize this. This right here, I'm going to call that an R and that an R. This is an acetal linkage. Over here, this one has an OR and an OR. Here it has an OR, but an OH. That means this is a hemi acetal. Comes from OChem, but do you remember adding a protecting group to a carbonyl and making a ketal or an acetal? Does that sound at all familiar? Do you protect them as a ketal or acetal? Perfect. This one, then I'm going to say is protected because it is 2 OR groups. It's like a double ether. This one is unprotected and it has an H. So first question, if it's unprotected, can it react? Yeah, you want to protect the carbonyl, exactly. So it's unprotected, so it can react and doesn't have an H to lose. So is this rich in H? Rich in H, unprotected, it's going to do its thing. This is then a reducing sugar. All of that O-chemists and biochemists do is so over the top to simply say, if it's a hemiacetal, it's a reducing sugar. This question, and I have to apologize again on behalf of all chemists everywhere, this question ends up on their practice materials, on their tests, fairly common. So this is actually a pretty critical thing to know. Reducing sugars are reducing agents that happen to be a sugar. They get oxidized. They get oxidized when you're rich in H and are unprotected. Hemiacetals are reducing sugars. So that's my take-home message from all that. And again, one of those small facts you put in your back pocket and you refer to down the road. But reducing agents that happen to be sugars are reducing sugars. Does this seem okay? And actually, how many have had this on a test or midterm or final somewhere in your travels in biochem? Or even OChem? One yes, two yeses, three yeses in private. Yeah, it just. So I will sort of go over it as kind of a hand wave thing. So let me say that a ketone, remember this, Bart Simpson, I drew the hair in, protects your ketones. This is an exposed ketone, this is a protected ketone. So what I mean by protected is it has an O and an O. So if it has two O's that are part of ethers, so carbonyl has two bonds of O, this still has two bonds of O, OR here and OR here. So this is an ether, RO carbon. This is an ether, COR, RO carbon. But when it's a double ether like this, it's called an acetal. So acetals and or ketals, depending on whether I'm dealing with ketone or aldehyde, are a protected form of the carbonyl. So when it's two ORs, protected. But when it's an OR, O connected to a carbon, on one side an ether, but on here it's not an ether. It's not a double ether. It's now an ether and an alcohol. It's a hemiacetal. It's just their nomenclature for it. So this is not protected. It's only protected when it has both of these. So that's protected, this is unprotected. Hemi for half, perfect. It's half protected. Half protection is not what you need. So you want your front door and back door both guarded. If it's only your back door, they can still come in the front or vice versa. Perfect. So how many are okay with this? You don't feel great about it, but it makes sense. At least it makes sense. You can make logic out of it. And if you see this question, you can BS your way through it. No pride, zero pride. Just pick right answers. Okay, moving on then. It's gonna, when I click, it's gonna go away. So if you're screenshotting, 3, 2, 1, boom. This one, I want to give you probably about, I don't know, 30, 40 seconds. So I'm going to get up and stretch a little bit. Sorry when you hear everything fall over. Okay, life is so interesting this way because I see these trucks have been working in the neighborhood like crazy on streets, and they're all parked in front of my house, but they're not doing anything. So I'm waiting. Hopefully we can get through lecture before they start making tons of noise. So I think we're lucky at the moment. So far, so good. Okay, for this one, it's identifying what gets oxidized, what gets reduced. So one by one, I need to go through these things. So help me out. How do I get the oxidation state of titanium in this? So you get it by difference. If I know that OHs are -1 each, so if you have two OHs and -1 each, titanium must be perfect, 2+. So I'm going to tell you then tungsten. So titanium is in fact +2. So tungsten, 4 bromides, so -4. So tungsten's +4. I feel pretty good. I'm doing great. You're happy with me? Am I screwing stuff up again? Dang it, same mistake I made again. Why 3+? What am I missing? The negative charge. So the -4 here plus whatever this is must be overall -1. The sum of the oxidation states must equal the charge. So -4 -1, that means it must be +3. Perfect. Everybody see what Jonathan put in the chat box? That is what I was too embarrassed to write because I figured my writing was so horrible. That's exactly what it is. Perfect. So charged molecules, I got to pay more attention. That's my mistake I make. Won't make it in the future. Titanium oxide. What is O? You've already taught me this, but I've already forgotten. 2 - 2 each. So if those are -4, titanium is +4. Anything by itself, what's the oxidation state? It's charge. 0 charge, 0 oxidation state. If it's by itself in +2, +2 oxidation state. So whatever it is, so 0, so 0. Perfect. Titanium then is doing what? Gaining or losing electrons? Losing how many? 2. It is being oxidized by 2 electrons. What has happened to tungsten? Oh, say it fast because I clicked too fast. Right, answer. Dang it. Sorry about that. That was my fault for double pumping the screen by mistake. But how many agree it goes from +3 to 0, 3, but it's gaining 3 electrons? So here's what I'm not sure. Does 3 equal 2? Are those the same number? Dang it, no. So you can't add electrons from anywhere else. You can't lose them anywhere. Everything lost here has been gained here. Quickest and easiest way to balance it, cross multiply. Take the 2 here, move it up here, multiply that. Take the 3 here and multiply it. So watch carefully as it happens. This 2 is going to move. So there's the 2. It's going to move up and down. That one goes 3, that goes 2. So the 3 goes here, the 2 goes up there. 2 times 3 is 6, 3 times 2 is 6, meaning I need 3 titanium species to be oxidized for every 2 tungsten species getting reduced. So I know it's got to be a 3-to-2 ratio, not a 3-to-1 or 1-to-3 ratio. 3-to-2, I pick choice D. I feel really good. I wait 30 days to get my score back. How do I feel on score day? Still pretty good by picking choice D. Zoe, what have I done wrong then? You're saying I got it wrong again? Why is it C? What have I done wrong? Did I answer the question or did I prematurely pick an answer and move on? Did I make a careless mistake by not reading the question and answering what I wanted to answer? It's subtle, and it's one of those careless mistakes. I attribute this to a careless mistake of thinking I see it and I know it and feeling overconfident because I've seen a question like this before and not reading the whole question. So titanium gets oxidized, so that makes it the oxidizing agent or reducing agent? Reducing agent. Oh, it's not a dumb question at all. How many are bothered by the fact, hey, we had some H's and BRs, where are they? So I've ignored them because I'm not fully balancing. So you've asked a really good question. Do I need to worry about the BR and the H to get this question right? No, but if I want to fully balance it, if I want an actual answer, then I have to realize on this side, there are 8 H or HBr minuses. And I have to figure out what happened to the rest then. So that's 2 minuses and 8 minuses. So I will need altogether then 6 OH minuses. If I'm doing in base, then I've decided it's base because there's a base there. So I have to go and I have to start balancing everything. So 8 minuses, 0 and 0, 2 minuses, nothing, and 6 minuses, so 8 minuses. Last but not least, I have to add water. So I have 6 plus 6. So do you agree altogether I have 12 H's? So I need to add 6 waters to this side. I am blowing through this balancing because why am I blowing it off and why am I blowing through it on this question? Why does it not matter? Why are you saying I just wasted time on this question by doing that? I feel better. Periphery numbers, that 6, that 8, and that 6 didn't affect the 2 to 3. So big picture, to balance it, what I needed to do, I needed to, number one, identify oxidation states and find the half reactions. That was first. Number two, I needed to cross multiply to get the balance. Number three, I needed to add in charged species. And then number four, I had to add in water to the correct side. So altogether, there was really like identify the oxidation states, connect the bridges, cross multiply, add charges, add water. 5 steps. But is it possible to get the right answer in just 3 steps, pick the right answer and move on? So the rule I want to follow is go only as far as I need to and be bothered by it, but let it go. So it's balanced because I have to have 8 negatives on each side. So the 4 bromines altogether times 2 means 8. So these 8 Brs are over there, but I'm going to just ignore it. Ultimately, we're doing all of it, but I sequentially do the bridge multiplication, the charged species, and then atoms, there's just cleaning it up with water. And it ends up in the video when I have on YouTube, I would highly recommend looking at that for balancing, because I'm totally shortchanging you right now on balancing. I'm saying balance it far enough to pick an answer. And I do mean that. In my heart of heart, I mean that as an important lesson for MCAT preparation. And I will say this, if they have one that has to be fully balanced, you're honestly better looking at the 4 answer choices and inspecting. Are the atoms balanced or the charges balanced? You'll probably be able to eliminate wrong answers. So knowing how to fully balance from start to finish probably is a great skill for chem, but not necessarily a useful thing for the MCAT. So the question just asked for that. So I'm done without the extra parts. But important to recognize, and I'm glad you did, but also if I answer that and say, yeah, that's how you balance it, in return, I ask you to make a promise to yourself. I will go as far as I need to pick an answer and I will move on, and I will not let pride ever get in my way. Moving on. What the heck's an EMF? Sounds like a small mythical creature. That's right. You guys are the generation that read all those fantasy novels growing up. So an EMF, is an EMF a small mythical creature with weird ears? Oh, it's an elf. Oh, shoot, off by 1 letter. So what is an EMF? Electromotive force. So figuring out what that term means. What does a force do? When I apply a force to something, if there's a net force on something, it's going to stay stationary, right? Object at rest stays at rest because you apply a force. Push-pull, it moves. It's going to accelerate. You apply a force to something, it's going to change its motion. If it's in motion, it's going to move differently. If it's stationary, it's going to start moving. Okay, perfect. So is this some force that can move electrons? Electromotive, electron moving force, a force that moves electrons? So if I did something as simple as this, you tell me what you think is going to be true. I'm going to put a metal with high electron affinity on this side. Then we're going to put a metal with low electron affinity. And then I'm going to put a piece of metal connecting them. And you give me a prediction. Do you think electrons are going to move from one to the other? Do you have a prediction of what might happen in this scenario? Why do you say yes? Which way are they going to move? Left to right or right to left? Perfect. The one with high is going to suck them over. The one with low is going to push them across. Okay, so make a few predictions for me. First prediction, The bigger the difference in electron affinity, you think the electron is going to move faster or slower? Faster. So I'm going to see if this is true. So I'm going to tell you electromotive force depends on the difference in electron affinities. So you're telling me electromotive force goes up. And what's the first letter in the word current? I've totally forgotten how to spell it. First letter in the word current is excellent. I. Perfect. You're spelling like a physicist. So, oh, yeah, you spelled it with a C. What were you thinking? First letter in the word current is I. Okay. Tell me also what you think. If the wire is very thick, a wide road, if you will, can electron flow more easily or less easily? Yeah, it's a current, duh, exactly. I'll put more easily, wider road. So I'm going to tell you that if resistance, oh, sorry, did not mean to do that in yellow. Not that it really matters, but I'm trying to stay somewhat color coordinated. Resistance goes down, I goes up. So combining these two, I'm going to tell you, here's what I think is true. I is proportional to EMF over R, which means EMF equals IR. So I want you to tell me, if you're sitting there and you're thinking, oh my, that's really important. Oh my, that's really special. What have I just come up with by making that observation? Yep, right in the middle of what seemed like a perfectly happy moment. And how many didn't say, oh my, how many said, oh, something else? Oh, blank. Well, yeah, did we just come up with Ohm's law? Meaning this is where it ties together. Hence, we don't call it EMF, we call it voltage, potential for a charged particle to move. So in essence, is that what we're dealing with? Am I now taking a chemical reaction, setting it up in a way where I can have an electron move over and harnessing that energy to be a voltage? This is where OCHEM meets physics. Every physics device you have, any electronic equipment you have, is run on a chemical battery of some sort. So in some way, somehow, you have a chemical battery carrying out the movement of electrons to engage in a physics process, whatever the machine is. Okay, so when I get right down to it, I went all the way from electron affinity. That's my starting point, my example. So can voltage, potential to move for certain elements, can that really be rooted back in just a periodic trend known as electron affinity? Or ionization energy? You can look at both, and it actually depends on a hybrid of both, but perfect. So how many are going to just memorize the periodic table and know where everything is? Or how many would prefer to be given a table? Ah, fine. Okay. When I was your age, we didn't have tables. Did everything in the dark on it with charcoal on a piece of metal. Okay. In your handout, is there a massive table? Yeah, in our cave. We just wrote with chalk at our cave. Yes, so what? Yeah, back when the earth was flat and there was only 3 elements to the periodic table, earth, wind, and fire, didn't have water yet. So is there a table in your handout? You bet. From that table, and when you look at it, are there a ton of entries and therefore a pain in the butt to navigate? So I want you to make some periodic trend-based decisions. For the alkali metals and alkaline earth metals, do they want to give up electrons or keep electrons? I forget. Do they naturally want to be anions, neutral, or cations? They're willing to give up. So notice, it's a reduction table. The table you're given, everything's a cation. So Na plus, K plus, do you agree? They're happy. They don't want to gain electrons. So therefore, notice they're very negative values. And so we run into our first dang you physics, dang you chemistry question, because physicists and chemists disagree on a basic tenet of life. Do chemists care about the chemicals or care about the world more? They care about chemicals. Hence, everything they define, all their numbers are based on what happens to the chemicals. Physicists care about chemicals, or they care about what they can take from the chemicals and put it into the world in terms of energy, work. They care about the world, so they have a different perspective. So if I have a chemical reaction that when you touch it feels really, really hot, would you conclude if it feels hot, it is giving you energy or taking energy from you? It feels hot, it is given you energy. The chemicals, the system where the chemicals are housed, gave you energy. To a chemist, they care about the chemicals. Do the chemicals gain or lose energy? Chemicals lost energy, so they would define that as exothermic. Heat is exit out, so they would define it as a negative energy because the system lost energy. To a physicist, they define that as positive or negative. Positive because they gained energy. Here's where the dilemma kicks in then. If I said something like delta G, the free energy, combination of enthalpy and entropy, is that a chemistry term or is that a physics term? Chemistry. If I told you about voltage, then what would it be? Physics. Because of that, because of the disagreement of chemistry and physics, the negative sign is simply for converting conventions. And I don't know, but when I had that revelation that chemistry cares about chemicals, it made all the sign functions in chemistry make sense because they never made sense. They were always counterintuitive. That's because I thought of myself as a part of the world. But as soon as I officially gave in and thought of myself as a chemist, it really just clicks like, oh my gosh, that's where the sign's coming from. It's just the heat is always hotter on the other side, kind of thing, just whatever you're looking at. But here's what we know then. Here's what I want you to tell me. From what you understand, when delta G is negative, is that favorable or unfavorable? Delta G is negative would be favorable. So what does that mean according to sign convention for favorable when it comes to voltage? So do you find a negative or positive voltage is favorable? Positive voltage, chemistry or physics term? Sorry to keep asking that question, but I want to hammer it early. Physics, so positive is favorable. So positive voltage is favorable. A negative delta G, because defined by a chemist, is favorable. So that sign discrepancy from one to the other is because one cares about the surroundings, one cares about the system. And luckily on the MCAT, if they ever ask you thermo, they are so kind and so understanding. They always ask system on surroundings, surroundings on system. They do not ever hang you up with a sign convention. Do not lose sleep or stress about it for the MCAT, but see it as a big picture. Okay, so that said, what do you expect then for aluminum? Aluminum, would it want to become reduced, or is it okay being a cation from your estimation where it is in the periodic table? It's okay being a cation, so it's if you force electrons on it, it's going to be unfavorable compared to H. So look at negatives. So how many notice it's around negative 1.66 in your table? Yeah, exactly. So the sign Stephanie just put up in the chat box, exactly, perfect. Okay, now tell me about silver. So is silver a precious metal? Silver is something that we use as a sign of value. Except for Jonathan when he goes to nightclubs. Sure, okay. So silver has value. So you do or don't want it to, copper baby, yep, me my copper chain. But yeah, so the bottom line, if you want to have something be a precious metal, a commodity, something that your like national currency is based on, you want something that oxidizes away or stays reduced. Exactly, stays reduced. So you would expect then the reduction of silver cation to be favorable or unfavorable? Favorable. You want it to be reduced, don't you? You like so, and again, the reason I'm saying reduction is if you look at the table, notice how everything is gaining an electron. So it's a reduction table. That's usually the way they do it. But Brooke, let me ask, as you're apologizing, let me ask you this. Do you totally know the logic and just happen to look at the wrong concept? Like happen to be thinking ionization instead of reduction? And it's easy to do. I mean, no need to say sorry. You know what it is. Yeah, so what? Say the wrong thing every now and then it happens. So I look at the table, I find silver to be positive 0.8. I find aluminum to be negative 1.66. The reason I took the time to go over that is if you can start seeing a trend, can you read that table faster? And so this is purely hypothetical, but let's say once upon a time in, I don't know, 1991, somebody were to sit and take the paper version of the MCAT way back when, and that, let's say 30 years later, the only thing they could remember from that experience when they sat there to take the test was this massive electrochemistry table with 34 entries that they only used like 4 of them, but had to work all the way through it. Would that be a testament that, wow, that table must have really traumatized them roughly 30 years ago? This is purely a hypothetical story. But yeah, that said, have any of you in your MCAT experience, if you've happened to sit for one, were you ever traumatized by a massive table? Like way too much information in a table, a drawing, every damn passage. Yeah, that's been kind of a norm since they switched to this format. So learning to navigate a table is critical. And that's why I wasted so much time doing it. Okay, notice everything's a reduction table. So are reactions red-red or red-ox? They're redox, reduction, oxidation, which means one of these has to be reversed. Because I'm dealing with voltage and I want the reaction to occur. Well, actually, no, actually, that's what I can do later. Because I'm dealing with a reaction, I need to match up. Is silver going from plus to 0 as drawn? So is this correctly drawn for what's happening in the reaction? So how many agree OH is -1, so silver is +1? So would you agree it is going this way? So silver is drawn right, but is aluminum going from aluminum to aluminum 3 plus, or aluminum 3 plus to aluminum? So is this one correct or backwards compared to what's happening? Backwards, so I need to reverse this. What happens when I reverse something to the sign? So when I go from aluminum to aluminum 3 plus, switch the sign. I have 3 silvers, so I have 3 here, so I need to multiply this times 3, don't I? I can't remember. Do I multiply it? And how many don't necessarily remember, but you have this kind of like, let's say there's, I don't know, the building's on fire and you hear somebody get out and you see like somebody in the window with a chainsaw. Should you go in or should you not go in? You don't go in, and in this one, you don't multiply because of intensive property. True story. My professor said that exact thing that you just said. You don't multiply because of intensive property. And further true story, I did exactly what Jonathan said. The one time I actually raised my hand to ask a question in class, I was unbelievably shy and not mean. There my hand was going up like, no, it was too late. Professor saw it, asked, and I said, what's an intensive property? And professor said, it's a property that's pathway independent. Doesn't matter the system, it's going to be the same value. Which I put my hand under my leg and never asked a question again because I was way too embarrassed to admit I had no idea what that meant. Okay, totally true. No idea what that professor said. So therefore, I needed to put in Todd speak. Todd speak is simple kindergarten to 3rd grade terminology that I can think of and water it down and understand. So here's the way I think about it. The subunits of a volt are joules per coulomb. So in this case, I'm going to ask you, if I get a coulomb 1 electron at a time or 3 electrons at a time, is a coulomb still a coulomb? Is it still a certain amount of charge, no matter how many or how few you get in a reaction? A coulomb is a coulomb. You don't multiply because it doesn't say joules per electron, it says joules per coulomb, a set amount of charge, meaning this has already taken into account the 1, this number is already taken into account the 3. It's joules per coulomb, so you don't multiply. It is an intensive property, and it is true. It doesn't matter what conditions you do it under. It's an intensive property. It's pathway independent. But what I'm more known to do, don't multiply because it's based on a coulomb, not on an electron. The electron, however, does end up here because this is joules per coulomb or joules per mole. Joules per mole, so I need moles of electrons. But for joules per coulomb, I don't need it. Okay, I'm not going to do well if I go into a meeting with a whole bunch of college professors of chemistry, but I'm going to do well in this dang test. Which is more important? Oh yeah, the voltage is an intensive property of the of whatever it is. So whatever voltage I get should be the same standard voltage I get under whatever pathway I do it. Whether I do it one reactant time, they all react at the same time, I should spit out the same amount of energy, pathway independent. Yep. And even then, even though I'm sitting here speaking it and saying it with a confident tone in my voice, I still to this day don't fully believe what I'm saying. And how many are guilty of that? How many are there things you know to be true, you accept, but if you really got pushed on it, you really don't know it? Perfectly fine with that. I've accepted that's who I am. I know how I can work my way through questions, and I keep my eye on the prize. Big picture, get questions right on the MCAT. And again, know as much as you can. Can I explain why I don't? Not at all, but I can get an thing. Exactly. Know as much as you can, be as interested as you can, and cut your losses when they happen. And for instance, if you ask me in the heat of the moment, do I turn right or left? You're going to see me go into the biggest panic you'll ever see me go into. I, for whatever reason, have that brain fart. The simplest thing, all of you can tell me right and left easily. Tell me about my hand makes an L, all those things. Makes no difference. It's just a brain fart. It's just something that I don't know why, but we have it. There's certain things, and so what? I know how to get right answers. So I added together 2.46. I want to mention this real quick, just a little side note. Are any of you old enough to have had silver fillings in your teeth as a kid when you got a cavity? So for the few of you who are in that category, I'm in that category. Did any of you ever inadvertently bite into foil with your filling? Did any of you ever take a chomp into some foil at some point in life? So how many would agree it felt wonderful? It was like the most amazing, gosh, wish I could do that a lot. Or how many would say it was painful, it was shocking and unpleasant? It is not one of the things you want to do because I know, try to figure out why would foil go in there. It's either occasionally you hit it with cheap silverware, that can happen, like electroplated silverware can do it. Or maybe when you make a baked potato and you poke the holes in, you have a piece of foil in there, you don't get it out all the way. It couldn't be that Brock's candy, which you probably don't know about, generation thing, was wrapped in foil and you didn't unwrap your candy because that's why you have fillings. It couldn't be that. It was I'm going with the potato story. The moral to the story, if you've done that, is this enough voltage to fire a neuron? See, here's where I'm confused and I need your help. I thought an action potential was like 60, 70, 90 millivolts. It depends on what neuron we're firing, but how many degrees? 60 millivolts, is that a reasonable number to throw out there as a typical action potential? 60 is way bigger than 2.46, isn't it? Please figure out where I've gone wrong on this. So I'm telling you 2.46 is small, 60 is a lot, so I don't know why it would fire. What error have I made? What massive error have I made that you need to catch? Action potentials are 60 volts or 60 millivolts. $60 millivolts. How many degree this is bounced over 3 times? 2460 millivolts. 2460 is more than 60. Is this enough to trigger a neuron? Oh yeah. So side note, once upon a time, maybe they might have had a passage talking about transplants. When you talk about a material you put into somebody's body, is it important that A, it's not toxic, B, the body accepts it and doesn't reject it, C, it's roughly of comparable hardness, flexibility, material strength to whatever you're replacing? Are these all the things that are important? Put a diamond in your tooth, it'll crush the other ones. Put a sponge in your tooth, it won't work as a tooth. You have to pick a polymer that's comparable to density. Okay, immune response, all that sounds great. One of the things apparently in early transplants they didn't pay attention to was electrochemistry. So the way you put something in the body, is that the way it's going to remain forever, or can it deteriorate? Can it oxidize over time? Deteriorates and oxidizes. So if they did, once upon a time, hypothetically speaking, a hip transplant with, let's say, a ball and a socket, So let's say that's the piece they put in. Hypothetically, they made the ball out of stainless steel. Hypothetically, they made the socket out of ceramics because those were big back then. Ceramics had metal in them. Stainless steel has iron in it. Over time, if this starts to oxidize even just a little bit, if this comes in contact with that, can you get an electrochemical cell where you have reduced tin, oxidized iron, and you get a transfer, electron transfer? I'm cringing thinking about it. Can you imagine being some of the very first patients to receive this transplant, and after about 3, 4, 5, 6 months, something like that, you take a step and you get this shocking pain right where you had that surgery? Unfortunately, this is an empirical study. This was not meant to happen. And all the things they considered, and you consider everything when you consider materials for a transplant. I'm sure you learned that in immunology. They forgot to consider this. So nowadays, stainless steel and plastic, they make it out of polymer. Why do they make a polymer? Yep. It's a different application, but basically, yeah, when you're going through a metal detector of some sort, you're going to set it off, give them a heads up. And number two, if you're getting an x-ray done, your privacy, so your HIPAA is being violated. So every time you go through the airport, your HIPAA is being violated if you have transplants. Just, I don't know if you really care about that sort of stuff. But I think that's the main reason why. Okay, and then the question again, why don't we multiply? Because it's already accounted for. So even though it's 3 and 1 in terms of electrons to balance, it's joules per coulomb, not joules per electron. So it's buried in the number. So if you will, this number has already accounted for the multiplication. This number is already accounted for the multiplication. I mean, the multiplication is built into it in advance based on the unit. So no problem, perfect. Okay. Oh yeah. So, oh yeah. So choice A is if you multiplied. Yep. Do they do that? Do they actually give wrong answers of that nature? So do you believe test writers are actually that mean and evil that they will actually take the time to figure out what a common wrong answer is and make that one of the wrong answers? So 2.46, choice B, but that's in there. So these answers, is this a case where they forgot to make it negative? So negative 1.66 plus this, we would have come up with D. Or if they reversed the wrong one, they would have come up with a different one. So do they actually do that? Do they predict what wrong answers will be and put those in? They do. Test writers are naturally mean, evil people who used to work as parking ticket givers. Oh, yeah. And actually, I mean, let me go in a different direction. Not only would you be given voltage values, you'd be given a massive table with a whole bunch of values you don't need. So one of the things that the MCAT does, and again, want to reemphasize this every chance I can, their approach is to give you all the numbers in the passage and then ask you a question, whereas in school, you were given the numbers in the question. So again, for those who've taken the MCAT, how many found yourself fishing through the passage to find numbers or units or terms or something fairly often? How many go back and had to figure out, okay, what was molarity and did we dilute it? And okay, we did. And what's this molarity now? Anybody find you had to do that? Take numbers in the passage and work with those. That's kind of a painful thing. True, but still painful. Some of us do like OChem. So here's my massive table. Got to learn how to work my way through it. Notice it's a relative scale. Everything's compared to hydrogen. So they just arbitrarily decide to say hydrogen is a 0. These are things that 1 electrons more than hydrogen. These are things that 1 electrons less than hydrogen. This equation, again, why the negative sign? Physics, chemistry, discrepancy in terms of thermo. So just negative delta G favorable, positive E favorable. So far so good. So a couple questions. It's not in the table. No, where do I get it? How do I get this number? I'm so sorry. I have my telemarketer receiver device still on noise making mode. From the periodic table, exactly. So where do you find lithium? First column, even though somebody already said it. So sorry, I should have recognized that. So how many agree you find it somewhere around those? Okay, so perfect. So is it a perfect trend or is it a rough in the neighborhood trend? Rough neighborhood trend. So what is a close estimate, albeit not perfect? -3. Perfect. It's got to be negative, like the other alkali metals. And then -3 is one a little bit closer. So hopefully it seems okay. So I know what you're thinking. You're thinking, gosh, could you throw one more of those at me? And I hear your silent cries. Negative or positive? Bromine does or does not want to pick up an electron. Positive, perfect. It wants to gain it, so we're there. And this time I only have one other element to compare it to. Let me make that circle bigger. So now I don't see a trend, I see an approximation. So now I have to make a trend. What's your prediction about which one would want the electron more, chlorine or bromine? Chlorine would want it more, so bromine you're saying is a little bit less? Okay, so Cl wants it more. Whoa, that was terrible writing. Br wants it less. So therefore, what's your answer? Size, definitely. Electronegativity, ionization energy, all of the trends. Every single one of those trends fits it. But the bigger it is, the less stable it's going to be when it picks it up. It's not as close to the nucleus. So size is definitely one way to look at it. Which is more electronegative? Cl. Cl wants it more. Another way to look at it. So the reality is, if you pick one trend to stick with, is it probably going to be true across the board? So when I look at bond strength, if I look at relative electronegativity, I'm going to be fine. But if I also look at relative size, I'm also going to be fine. So the periodic trends kind of are cool that way. You can apply one of your favorite. So in this case, 1.19. Table reading is key. Okay, how many would agree? I kind of gave you reasonable ones. Just basically find something on the table. So how would you rate that question on a scale of medium, easy, hard? Oh, it's not really a scale. I'm all over the map. Medium? Okay, secondary application, fair enough. So what you're saying to yourself is, but what we really want, give us a hard question to screw with us. Particularly, it'd be great if you could make it a tricky question to make us feel bad about ourselves. And again, who hears your cries? Who hears your needs? I do. I do. I'm not going to answer. I mean, as people sent me private and public messages, and so I'm going to just hold off a little bit. So the question I want to ask you, how many of you are using the numbers in the table? Am I safe in assuming they gave me a table, I must use it? I want you to start thinking in a slightly different fashion than that. So the test writer gave you a table. What we learned earlier, do test writers write intentionally wrong answers? Do they write answers that they know people pick that are wrong? Okay. So if they give you a table, chances are you're going to use the table. So good call. I'm going to give you things that are really screwy. So I'm going to ask this in a totally different way and see if we can get this. Strongest oxidizing agents. Oxidizing agents get reduced or get oxidized? Get reduced. Perfect. Getting reduced means to gain electrons. Does that want to gain electrons and become gold minus? Do metals ever want to become minus? Doesn't happen. Which one is happy with a plus charge? K plus or palladium? Happy with a plus. That's my answer from a periodic table standpoint. How many of you agree, damn, that was easier to think about it from a table standpoint, definition standpoint, and periodic table standpoint than it was their table? Conceptual answers generally are I know, feel better than math answers. I have to be able to do it by math, but that's the right answer from a concept. Okay, just to say it, every single person who put an answer in chat got it wrong, which means, are there some hurt feelings right now? Like, how the heck did I mess that up? That is totally fine. That is part of the growing process. This was a trick question designed to make you miss it and feel bad about yourself so that you can hopefully grow and become a better person that doesn't make that mistake in the future. So one thing I learned, wow, if I would have done it by just thinking about it periodically, I would have been fine and gotten it. And now I want to make sure I get the math answer. Okay, strongest oxidizing agents get reduced. So would it be Au3 plus or Au that we should be looking at? Au3 plus. So Au is already reduced. So Au3 plus has the 1.5, not Au. So next on the agenda, PD2 plus. That's looking pretty good. FE's on the wrong side. So that's out. And K plus on the correct side, but too small. So a positive number, the most favorable one of everything that I have on this side, is 82 plus. So I feel okay about this one, but again, if you got it wrong, so what? It's what you learn. So hopefully it seems okay. So let me go ahead and mess with you again. If you want to screenshot it, do it now, because I'm going to click and something else is going to change on it. So 3, 2, 1. So these are my 4 reactions. So again, Au, Au, wrong side. PD, PD, check. Iron, iron, wrong side. K plus, right side. That's your best answer. Okay, see you Sunday. Sorry it's going over as always. And I think these Friday ones are probably going to go over. Yeah, and so why is it so much easier to see? Because I have the 4 things I care about instead of having to navigate the table. And you nailed it. The MCAT would be so much easier if they only gave you just what you needed. And unfortunately, in school, did they give you more than you need, exactly what you need, or did they give you less than what you need and you had to do it for memorization? in most of your tests. Less than what you needed, you had to count on memorization. Now all of a sudden you're taking a test that's going the exact opposite way. They're giving you a deluge, an overload of information, and you have to navigate and decide what's important. And it is flipped, and it takes a while to get used to. And it's like, seriously, you're right. When I go from the massive table to just the simple table, ta-da, I totally get it. So I can make this question hard in two ways: give you too much information or not enough information. They go with the too much information route. But if I know that, I can prepare for it. I'm so ready for this test in 3 months. Or somebody said yesterday, 99 days. I couldn't believe it. As soon as they got British for the test, was it one of you who actually posted that? I should probably, before I say this, before I laugh at you, I should see if I'm laughing at you or with you. Yeah, and it's just, I mean, it's a natural thing. It was, okay, yeah. So I'm sorry, so we're just like, yep, it's just, that's life. That's how we think about it. You had 98 today, that is true. We did have a nighttime turn to daytime again. What? Yeah, but you know, it's on. No worries. Okay, for this one, strongest reducing agent, meaning we're looking for the forward or back reaction. Now we're looking for the back. So in this case, I want to match the sides. So let me do the same things before. I'm looking for Cl2. I need to be on that side, wrong side. Nickel. So that's on the right side. Aluminum 3 plus. I need that one, not that one. So that's out. And then magnesium on the right side. Reducing agents get, so we're at that point. Let me redo my circles. Now the table's been simplified. So Cl2, wrong side. Nickel, correct side. L3 plus, wrong side. And then correct side. Most negative value, exactly, because reducing agents get oxidized. Therefore, best back reaction. The best back reaction, positive number. And you switch the sign, exactly. Why do you switch the sign, Brooke? Anytime you reverse a reaction, you change your signs. Except for K equilibrium, you invert. Products or reactants become reactants over products. But for everything else, change your sign. Okay, so table reading hopefully is okay. I'm guessing about another half hour. I'm apologizing, this is going slower than planned, but I'm hyper cognizant of the fact that this is being possibly something to be pushed in the future. Ah, perfect. Okay. Electrochemical cells. What is the whole purpose of an electrochemical cell? Exactly. To give you energy. How many agree your car wouldn't start without a battery? Your engine wouldn't operate without fuel to give you? Your cell phone wouldn't work. My computer wouldn't work. We have to give energy somehow. So electrochemical cells are designed to run two ways. Release energy, known as galvanic cell or favorable cell. But then, do you recharge it? So for instance, if your phone runs out, do you just throw it away and buy a new phone? Or do you plug it in and recharge it? Okay, so you put energy in. So does that mean electrochemical cells have to be able to run just in a discharging, energy releasing fashion? Or they have to be able to run in a recharging fashion? Oh yeah, you have to reverse all of them in the last question. So the question was, do you reverse half reactions for all of them? Yeah, because the question was asking for the best reducing agent, and reducing agents get oxidized. So you're looking for the reverse reaction, because all the reactions in the table were reduction. Every single thing in the forward direction was gaining electron, so we had to push it back in the opposite way. So does that make or seem okay? So for all four choices, we had to push it backwards because the question was for the back reaction. Okay, galvanic cell. The goal is this. Do you want charge to move and build up, or do you want charge to move in a giant circle, which is actually the way you make a circuit? Flow from one point to another and stop, or flow all the way around a circle, and it's actually the motion, the friction, that's giving you the energy. So interesting question. And actually, this is one of those fundamental thoughts when you realize that it's like, I get it now. So when we talk about a circuit, how many agree it has to go all the way around from one end to the other? Or is it from one point to another? And that's what I'm going to leave that as an open-ended question, and we're going to discover the answer as we go through it. So sorry, you know what? I'm becoming that teacher I hated. I hated when teachers did that. But it's one of those things. Question to start out with and decide what's happening. So I'm going to tell you there's actually two paths I have to worry about. We already talked about one earlier. Do electrons go from anode to cathode or cathode to anode? I can't remember. But luckily, you're here to help me out. Alphabetical. Electrons flow alphabetically from oxidation at the anode, oxan, to the red cat. Perfect. Alphabetical A to C. Everybody nailed it. So oxidation occurs at the anode. So electrons are going to flow from the anode, oxan. And just out of curiosity, which electron is going to move the fastest? This one here, that one here. Maybe we could turn this into gambling. Just you know, that'd be a lot of fun, wouldn't it? Electron races. Which one moves the fastest? Okay, weird question. Last one on the right, possibly. Closer, cathode, maybe, could be. So I'm going to ask you a different question. Have you ever been to a theme park in your life? Like a Six Flags, something. I mean, there's basically Six Flags everywhere and you turn. So how many of you ever been to a theme park like a Six Flags park and you're waiting for the roller coaster? Is the line super fast in front, slow in the middle, and slow at the end? Super fast in the middle, slow at this? All the same. Either way, you look at anybody, the front line, middle line, or end line, they're all moving at a snail's pace because they are in series or they're in parallel. Series. In series, you can only go as fast as the person in front of you gets out of the way, and the person behind you can only go as fast as you get out of the way. So in series, current, the flow of charge is the same. But once you get up the turnstile and you agree you choose left or right pathway, how many agree then it's different and you always choose the slower one? Perfect. So now you're moving in series or parallel once you split at the gate. Oh, driving on the freeway, all of it. So how many would agree that once you get in a different lane or a different pathway, a different whatever, you're in parallel, then you move at different speeds? So in series, current's the same, flow charge is the same, but in parallel, you can have different flow rates. Path of least resistance is a case where you have a choice or have no choice. When I say path of least resistance, it's when I have a choice of more or less resistance. More things will choose a less resistant pathway in parallel because it's faster. So are these in series or parallel, all these electrons? They're all in series, meaning they're all going to move at the same speed. This one's going to do something cool. This one's going to do something cool, so you can watch them. But I'm going to click in 3, 2, 1. Wow, that's replay material. So yeah, thank you. So the pain in the butt why I can't give you slides and because it's animation is because of that totally pointless thing that I'm so in love with my Macintosh for being able to do such a thing. But they all move at the same speed. So what happens then is you start crewing electrons. Do electrons go into the solution to go swimming, or are they bound to the metal? They're bound to the metal. They cannot go into solution. So if love is going to happen, if a cation is going to meet an electron and fall in love, does the electron have to move to the cation, or does the cation have to go to the electron? Cation has to move to the electron, and when it does, it picks it up, turns into a metal. It's no longer soluble. It will plate out on the surface. Hence the term we mentioned earlier, electroplating. So it's working out. I'm liking this. So second thing then, Electron flows anode to cathode, number one. Number two, reduction occurs to the cathode. The cations, this metal I have shown here, is going to go to the surface and pick up an electron. This metal here is going to go to the surface, pick an electron. So I'm going to start building up a thin layer of plated out metal. Kind of like sugar crystals, except this is gaining an electron, that is just crystallization, but yeah, perfect. They keep on building like on that string. Sugar molecules in solution have to go to the string can't go to the sugar molecules. Perfect. Really good analogy. Why do you make analogies, dang it? Because they help. Because it makes it easier to comprehend. By all means, analogies, the more analogies you make, the more you're going to remember. The more you can apply it from one situation to another, the better you're going to do on this test. So take that small few seconds to totally celebrate a really good example you just gave, and then we'll move on. But oxidation of the anode, reduction of the cathode. Oxan. Leo, lose electrons. The red cat, reduction occurs to the cathode. Says GER, gain electrons at the for reduction. Okay, I'm happy with this. So far, so good. What is a salt bridge? Is that a bridge made of salt? Let me ask you a more disgusting question. Is a footbridge a bridge made of feet? That is so horribly disgusting when you think about that question, but hopefully not. Why do they call something a footbridge? Named for what it's made of or what traverses it? That which traverses it. So a salt bridge is named a salt bridge because it's made of salt or it allows for salt to transfer. Okay, so for the electrons, they have a distinct starting point, the anode, and they go to a distinct end point, the cathode. But the problem is in this solution, you end up having metal plating out, turning into cations turning into metal, but the anions that were with them start building up in excess. That negative charge in solution that starts building up with no partner anymore causes repulsion. And so just like electrons have to be on the wire for conductivity, electron is another hit another, hit another, hit another for it to go. So that's why conducting materials with electrons that can move work. This has to be a pathway that has chlorides that can migrate. So we'll ask this question again. Which chloride is going to move fastest? This first one, this one here, the last one? All the same because one massive series pathway. It's just one giant series loop. Exactly. So salt cations are going to go this way to the cathode. Anions are going to go to the anode. So what is your question? Oh, you stole my question. So if I were to say I hate you, that'd be wrong, especially if it's recorded. So I'm going to say really good question, but deep inside I'm thinking, dang you for stealing my question. But exactly, perfect question. Which goes faster? Electrons going this way or chlorides going the other way? Same. Series, so it has to be the same. So this is part of the reason why batteries don't drain instantly, because electron may be able to flow really fast, but it's the Cl minus what's messing things up. Cl minus migrates slowly, so electrons have to migrate slowly, which means do batteries run out instantly or do batteries take a long time to drain? Yep, the flow is for one circuit. So individually, electrons have a start and finish line, and chlorides have a start and finish line, but overall, it's a giant loop. That was the answer to the question that I didn't answer at the beginning because I didn't have an answer. The answer is what we're looking at. Overall charge flow is cyclic, but electrons are anode cathode, anions are cathode anode. So a couple rules. Everything we just did, I want you to hang on to. There are three things that become key. Cations go to the cathode, anions go to the anode, electrons flow alphabetically. So these three things, I want you to just commit to memory, write it on your arm, get a tattoo, say every day when you wake up in the morning. This is going to be true in electrophoresis. This is going to be true in electromagnetism, electrostatics, when we do magnetic or electric fields. Magnetic fields have poles. They don't have anode and cathode. They have north and south, so I apologize for that. But electrostatics, electrophoresis, electrochemical cells. So instead of worrying what charge it is, I'm going to hang on to this. So I want you to take these rules and apply it as follows. You know, it's really interesting why I italicized it, because honestly, I ask myself that every time and I forget to unitalicize it. I think it's emphasizing the fact that for whatever reason we call it flow, because it randomly flows across a wire. Migration degree is a group moving across, but some can go different ways, whereas these flow, they're always going the same direction. Ions in theory can go both ways, but you have a net migration, net movement. So I think that's why, because it is a word that's said in like straight out of textbooks. They migrate, whereas they flow. So the flow goes one way. Migration, in theory, you could have both ways, but the net migration. Okay, key things I want here. Okay. The rules: electrons flow anode to cathode, check. Anions migrate anode, check. Cations migrate cathode, check. These are the three rules. You know them. You believe in them. So you can answer these questions in a second, because I don't know my slides very well. Which one is which? I know one is the anode, one's a cathode. I can never remember, and I need your help. If only I had seen this movie when I was a kid, like probably all of us did, because they remade it way too many times, called Little Orphan Annie. And I could remember Little Annie and know the little one, and there was a character in there known as the fat cat. So I could know the fat one, the wide one is a cathode, and Little Annie. If only I could remember that movie, Little Annie with the fat cat. How much pride do I have? None. So therefore, that's how I remember it. Embarrassing to admit, but Little Orphan Annie, fat cat. Here's my discharging battery. The anode is connected to the cathode. That's a cathode. Cathode connected to an anode. So this anode connected to a cathode plate, this anode plate connected to a cathode. Okay. Electrons flow alphabetically. Electrons are going to flow from anode to cathode, anode to cathode. So here's what I'm going to get. Electron flow, anode to cathode, check. Number two, if I were to lose electrons from here, the residue would be positive because I lost negative. If electrons flow here, the residue would be negative because it builds up negative on the surface. So if you were to place a charged species in the middle of this electric field and put a gel in it, we're doing gel electrophoresis. If I were to put a negative charge, an anion, how many agree the anion would migrate to the anode? Cation would migrate to the cathode. Are my three rules being applied to an electrophoresis apparatus? Are electrons flowing anode to cathode? Check. Anions migrate anode, cations migrate cathode. To make my life easier then, when I do gel electrophoresis, do I study cations and anions, or do I make everything an anion? Do I study DNA, which has a phosphate backbone, RNA with a phosphate backbone? Do I add in SDS to the protein to give it a negative? You want to run in a single direction? You make everything an anion. So you load your wells over here, and all those anions go to the anode. Pretty much standard. So everything we do in electrophoresis, make it an anion or use an anion. Okay, feeling pretty good. So with that in mind, I went and answer some things for me. Which way does DNA migrate in electrophoresis? You have 5 seconds. DNA carries a negative because of the phosphate backbone. Anions migrate to the anode. Migrates from the cathode to the anode. Question number 2. Where do palladium cations get reduced? Where do positively charged cations get reduced? So I'm trying to figure after that, my brain blank next game. Oh, not gonna lie. Okay, perfect, thank you. Where do chlorides gather? Where do chloride anions gather? Anions go to the anode. Perfect. Follow the rules and don't, it's easy to get caught up. What is the charge of a plate? What is the charge of the battery and all that? Let that go. Focus more on what happens to cations? Cations go to the cathode, anions go to the anode, electrons flow. I just realized that sentence, I'm glad I said it at the pace I did. Focus more on this, as opposed to say focus more on. What I said was focus more on this. So sometimes those things pop out the wrong way. Yeah, no, focus. Forgot the focus part. Perfect. Copper zinc cell. Look it up in the table. You get zinc is a negative 0.76. Copper is a positive 0.34. You reverse the zinc from positive, so you end up with 1.10 volts. That's from the table. So I'm going to ask you to trust the math and worry more about the setup. So zinc got reversed, so zinc is now going to be, instead of reduced, it's going to be oxidized. Where do you put the zinc then? You put the zinc in the anode or cathode if it's getting oxidized? Perfect. Zinc anode, copper is getting reduced, copper cathode. You only need reactants, meaning to make this go, I need zinc solid, I need copper 2 plus. The presence of zinc 2 plus, a product, will help or hurt the reaction according to equilibrium. So the presence of a product makes it go more in the forward direction or less? Less. So the more you let zinc 2 plus build up, it's actually going to repel it's going to push back and want to get plated out. So concentration matters. And then I need copper 2 plus. It doesn't matter if this is copper metal or anything conducting. I'm going to copper plate it. Chloride is going to go this way. So overall, I'm going to have electrons going this way, chloride balancing out by going the opposite way. So again, which electron is going to move the fastest? All the same. What's going to happen to the cations? Cations are going to go here. So cations go to the cathode. This cation is going to go here and pick up the electrons on the surface, get reduced. This is going to turn into a cation by moving away from the anode and towards the cathode. So that one went there, plated out. This one came out. These excess chlorides are going to repel their way back the other way because anions are going to go to the anode. Perfect. Hopefully this is all falling into place. Okay. I've noticed that the numbers going down. That's fine because I'm sure most of you can come back and possibly revisit this in the future. So sorry it's going over time again. Wanted to be slow and methodical. I will get faster in the future ones. Over time, you plate out, you build up the cathode, you dissolve away the anode. Hopefully this all seems okay. Okay. Electrolytic cells. I mentioned that your battery is going to eventually run out on your cell phone, your computer, whatever it might be. Would you agree? Okay. So you recharge it? In what way? How do you recharge it? How many of you plug it in? I mean, how many would agree with this? So I want you to explain a few things to me. If I set up a battery like this, if I did this in physics, if I drew my circuit like this, would physics people be upset or happy with my drawing? They'd be upset. I hooked up an anode to an anode, cathode to a cathode. I'd be penalized with points off and a sad face. Should be anode cathode, anode cathode. But make a prediction for me. If that's 2 volts and this is 1 volt, which one's going to win? 2 volts going to win. So electrons are going to go this way. And therefore this way. And so this reaction is running the way it wants to, or is it now being forced to run in a negative fashion? Forced to run in a negative fashion. So if I were to apply a larger voltage here, can I force a reaction to go backwards? The physicist is pissed off at you, but did I just recharge my battery? So in order to recharge your cell phone, you have to plug it into the wall, but one of the conditions, does this have to be higher? It just reversed. It forced itself. So what used to be the anode is now forced to be a cathode. What used to be the cathode is forced to be the anode. So you forced it to go the opposite way. So electrolytic cells are ones where you apply a voltage and you force what used to be the cathode to be an anode, what used to be the anode to be a cathode. You force them to do the opposite. So, quick question for you. As long as this is higher, so let me do this in real life. We have 110 volts for our outlet. Let's say your cell phone is 4.5 volts. That's plenty. 110 is going to recharge pretty much anything you have, anything from 4.5 to 12 volt portable devices. You're good to go. How many have ever visited this place called Other Country? Anybody stop by there for a brief stay, a day, couple weeks, year, month, half a life? I'll be honest, I visited Other Country before. And what I noticed is that pretty much every country, except for those of us in North America that have 220 volts instead of 110 volts. I mean, how many would agree with this? Yeah, we're pretty much the only one that has this weird one. Oh, you don't leave your cave? You don't believe in electricity? So I believe there's something called V equals IR. So if I build a device with some resistance X, and I'm building it to be used to 110 volts, then I get a certain current. Probably the max it can handle. What happens when I go to this place called Other Country and I plug it into a 220 outlet? Same device. So current has to double. Is it now beyond what it's used to? Your battery could explode, but more common thing, it literally catches fire. Your device, because of all this current means all this heat means fire. My youngest daughter, bless her soul, brought a hair straightener. She wanted to show off her new hairstyle to her cousins, plugged that thing in, and within seconds, it was so hot that I burned my fingers trying to unplug it. It gets really hot. So Brooke has a suggestion. Brooke said, what should you do? Yes, this is why we do gel electrophoresis, use converter, because 110 versus the 9 volt that you normally want to use in electrophoresis runs it down. So what Brooke said was use a converter when you go. You said use converter when you're in lab. All these things are true. But tell them about a converter. Converter stays cool, or does a converter also get really hot? Get super hot because is it taking, when it goes from 220 down to 110, is it doing it by taking energy out of the system, by lowering the voltage? It's taking it. So your device doesn't catch fire. The transformer is built, or the converter is built to do this. So does that seem reasonable then, why different appliances? A whole bunch of theories why we have different appliances, but the going notion was that our products weren't competing well, and international products were outselling us. And so we changed the voltage system here so that we had our own. Yep, that's how heaters work. So let me ask you this. What usually blows your circuit breaker? Tell me all the usual offensive things that break your circuit breaker, trip your circuit breaker. Microwave, hair dryer, space heater. Exactly. 3 things you guys typed in. Are those all things that you convert current into energy? So if they're draining too much energy out, if they're draining too much current, pulling too much current, because you have a lot of current, the more current you get, the more it drains. If they overheat, if they draw too much current, then the circuit itself can possibly overheat. So it trips to avoid that. But yeah, usually your big offenders are the big power drainers. The big power drainers are the ones that are sucking all sorts of current. It's kind of cool. So next time you're blow drying your hair before you don't leave your cave, now you know. I'm waiting, Brooke. I can explain his hairstyle. Oh, okay. Oh, why the voltage has to be double? It's always designed, or why it's double? It's basically because if you're trying to cut the voltage in half, then your current's can end up being double, because if you're dealing with double the voltage, it's going to relate to double the current, if that's what you mean. So wattage is, oh yeah, wattage is the capacity. So let me go back to this. P equals IV, or P equals I squared R, either way you want to do it. So your wattage, because of the square this way, or because it's a product of these two. So your voltage and your current are both going up, so your power is going to go up that way, or resistance to the device is the same, but current squared, so you want it to balance it out. I think that's where it comes from. So yeah, so you always want to, you want to make sure your wattage, because that's your power. Wattage is power, energy per time. So hopefully that makes sense. And I cannot explain Jonathan's hairstyle. That's just, that one good luck. Okay. See, this would be such a better smart aleck comment if we were in person. Okay, I have my thing on erase, so if you're going to screenshot, do it quick, because if my hand moves, it's like one of those thumb triggers. So erasing in 3, 2, 1. Electrolytic. Electrolytic is unfavorable. How do you get an unfavorable reaction to go? So in biochem, if you have an unfavorable step in a pathway, what do you have to do to get it to go? Add energy. Couple it with a reaction that releases energy. So same thing here. How do I get an unfavorable reaction to go in this circuit? Couple it with a favorable. Add energy in. So if you see a voltage source or any sort of power supply, that's your dead giveaway. It's electrolytic. You're forcing it to go the other way. So notice, before I drew my anode on the left, drew my cathode on the right, but now with this voltage source this other way, I'm forcing it to go the opposite way. Oxidation still is occurring at the anode, reduction is still occurring at the cathode, forcing it this way. Electrons are still going from anode to cathode, anions are still migrating to the anode. I've changed a couple words. So notice I call it a membrane. How many, when you see the word membrane, you just can't help yourself, you automatically say semi-permeable? Just what you do and just how we are. Semi-permeable means only anions can go across. Hopefully that seems okay. But the key thing, the take-home message I want you to see, if you see a battery or voltage source in a circuit, is it electrolytic that's being recharged, or is it galvanic, which is discharging? You see a battery? It is said to be an electrolytic cell. When you plug your cell phone or your computer in, you are making that battery an electrolytic cell. When you unplug and you're just running it, it is now a galvanic cell. That battery is giving you the energy to run on, but you're recharging it. So basically electrolytic, you're recharging it, so it can actually go the other way. So big picture of this one. So screenshot, if you will, I'm about to click. 3, 2, 1, clicking. Okay, swear something more important was going to happen. Here we go. So my battery ran dry. I ran out of zinc, and I have this big mass of copper over here. So I plug it in. I apply voltage. Teach me what's going to happen. Little orphan, I can't remember. Little orphan Kathy or little orphan Annie? Little orphan Annie. Therefore, this is the anode, making this one the cathode. Which way are electrons going to go then? So that is the anode, that's a cathode. Perfect. So red cat, oxan. Reduction is going to be the buildup or breakdown. I can't remember. Reduction builds things up or breaks things down. Reduction builds up. Oxidation breaks down. So we're going to play it out here. This is going to get bigger. This one's going to get smaller. I'm basically going to turn it back to what it used to be. Which way is charge going to flow then? Through the membrane. Anions are going to go to the left or to the right? Anions go to the anode. So anions are going to go to the anode. Electrons are going to flow back the other way. So negative in the form of electrons is going to go in this direction. So electrons flow alphabetically from anode to cathode. Anion is going to migrate this way to the anode. So predict what you expect to see. Do you expect to see an overall counterclockwise or clockwise flow of charge as drawn? Counterclockwise, perfect. The sad faces are totally acceptable, by the way, that pop up in the chat box, because it takes a little while to get used to looking at this way. Again, am I asking you to look at these things different than the way you learned in school? Trying to see the big picture. It's kind of a challenge because I'm teaching chemistry, physics, biochem, and GChem all stuff together. I probably said chem more times than I should have. But you're being forced to learn them all in one collective block. So pick it up piece at a time, like a dance. One step at a time, go slow, methodical till you get it. But anions go to the anode, electrons flow anode to cathode, anode to cathode. This plate's going to get bigger, this plate's going to get smaller, these are going to go this way, this is going to go this way. I'm going to erase everything I have written so that you can just really enjoy that Macintosh animation. Thank you, Apple. So erasing in 3, 2, 1. And here we go. Watch this amazing event. Wow. Charge did go counterclockwise. This got bigger, this got smaller, and now it's recharged. And now I can unplug and go enjoy my life before I have to replug. Does this make sense that the voltage here must be higher than the reaction voltage and why it flows the way it flows? So the non-animated form is going to pop up. So 3, 2, 1, clicking. So key thing, electrons flow this way, chlorides flow that way. This is now a negative. This is now unfavorable, so it's negative. So overall, it's a negative 1.10 volts. So I must apply greater than 1 volt, greater than 1.1 volts. Okay. Have I hit the point of exhaustion for any of you? Have I just hit that fine line where you went from totally getting into it to now that fatigue state? It happens. I mean, you can just feel it. Just basically the chat box sort of feels it, the energy that's coming back out of it. So going to do that finger stretch, shoulder stretch, deep breath, and hang on for about a couple more minutes. No, don't be sorry. Actually, the chat box is awesome. The chat box, again, I think I've said this, but the chat box was freaking great when we went from a live in-person, never ever would do anything online. It was the devil to us, to suddenly being forced to. And the shy student who never spoke up at all in class, suddenly with private chat, she was just on it. I realized she was a genius. She knew so much. And the chat box was the saving grace. It was pretty awesome. It was really, really cool to discover that. Okay, so that said, copper dissolves away over time. Zinc plates out. So you had no, it doesn't look like it dissolved away, but it got smaller. And anodes get smaller, cathodes get bigger. Okay, this was purely for screenshot to summarize everything. Clicking to a question and 2 more things and we are done. 2 more things are actually pretty straightforward. So in the Nernst equation, basically, I want to revisit something that apparently is a biochem main staple. And I just want to visit this by making note that it's actually that. And here is what I want you to note. This is where it is. That's an IS, not an I5. This is where it wants to be. And this is how much comes out of it or goes into it to move it from where it is to where it wants to be. So simply put, if you're at equilibrium, what is delta G? If you're at equilibrium, it is 0. You are not moving. There is no exchange of anything on the whole because you're where you're at. So therefore, if this was equal to K, then minus RTLN of K plus RTLN of K would be equal. But if you're not at equilibrium, you agree this trying to get to K is going to dictate everything. So again, I like this one. If that's the case, you move backwards. So delta G would be a positive number. If that's the case, then the arrow would go this way. So it would move, oops, sorry, I wanted to switch to green. So this would mean delta G is a negative number because forward is a negative. Want to just go off on a tiny, tiny tangent, and I think you know where this is coming from, but why do they say if you, as a biological system, if your body is in equilibrium, why are they saying that can only be possible if you were dead? They being, let's say, professors and PhDs. You don't have any gradients, nothing has any net movement. We are not a stationary thing. We aren't putting energy in, we aren't doing anything. We are a steady state. What goes into us and what comes out of it? Well, that's what the people correcting him meant. I'll leave it at that. So we take in O2 and we spit out CO2, which means the minute we take a breath, we're putting O2 in. So even if we were at equilibrium, we put O2 in, that's going to push another reaction forward, which creates excess there, which is going to push another one forward, and eventually do we get to CO2 coming out. So we are technically a steady state. Homeostasis literally translates, okay, maybe I'm exaggerating, but it's close to saying a steady state, a steady condition, where we take in O2 at a given rate and give off CO2 at a given rate. And in all these little steps and going through this process of food and O2 in, CO2 and other waste out, we are generating the energy we need to function. Equilibrium is a closed system, forward and back the same. Steady state is something that keeps on moving forward at a constant rate. So you build up specific quantities. So this is being made and used up. This one's being made and used up, made and used up. So we get intermediates that look like they're in equilibrium, but instead they're in steady state. Formation equals consumption. Formation equals consumption. But O2 food in, CO2 out. If you stop, you're done. So what are K and Q? You tell me what K is, I'll tell you what Q is. Let's meet halfway. So what is K? Besides your last initial. K is the equilibrium constant, the product to reactant ratio within the rules of math that you square your stoichiometric coefficients of where it wants to be. So K represents equilibrium, what it wants to get to. Q is the same calculation, product to reactant, but not at equilibrium. Because we are not at equilibrium, because Q is not equal to K, do reactions keep moving? Does energy keep on getting generated, and do we keep on existing? If Q equals K, if they're one and the same, we stop moving. We go back and forth, but we generate no energy. We have no gradients. We can't take ions out of our system. We can't move things from point A to point B. We cease to function. We are then a zero delta G entity. So hopefully that makes sense. So it sounded like a lot of you have been told that in biochem class. How many had a biochem professor who said that if we were at equilibrium, we'd be dead, that we're a steady state, or something like that? Oh, actually, cell bio, is that where they say it? I had a biochem professor who was more of a philosopher, and that's the first time I had heard that and thought, yeah, it's an interesting thought. So equilibrium closed system, steady state, open system. Things feed in, things come out, and you have this sort of consistency that things are made and consumed at the same rate. So you have seemingly constant concentrations appearing like an equilibrium, but it's actually a steady state. So to those of you who piled on in the chat box, you were all right. So hang in there. Okay. So this equation, does this, oh, you're welcome. Does this apply to everything? Or is this only for electrochemistry? This is basically everything. So when you knock a system out of equilibrium, it wants to move to equilibrium. And when it moves, you get energy. Nernst took this and said, let's divide a lot of things by NF and a negative. And let's make one term super ugly, but two terms a little bit easier to deal with. So delta equals negative NFE. So dividing, this is an E. This is an E naught. So this is the same thing. The voltage you get out is what it wants to be and what it actually is. That's all this is saying, is that Q wants to eventually become K. Where you're at, you eventually want to get to equilibrium, and the energy or voltage associated with it comes from that. Okay, what I care about, deriving this thing is the most pointless adventure we ever did. I went through it because I kind of wanted GChem. In physiology, we deal with millivolts, and GChem, we deal with volts. So in GChem, I care about that term, E equals E naught, and I just usually ignore it. This is trivial. But in physio, when I tell you about sodium and potassium, is that pretty much what